In the vast expanse of the universe, where countless stars are born, live, and die, there exists an enigma so massive, so powerful, that it bends the very fabric of reality. This isn't a science fiction tale, but a true cosmic wonder known as TON 618, the most massive black hole ever discovered. With a mass 66 billion times that of our Sun, TON 618 is a true titan, a force of nature that defies imagination and challenges our understanding of the universe. But how did such a gargantuan entity come to be? What secrets does TON 618 hold about the origins and evolution of black holes? And what can studying it teach us about the nature of space, time, and even gravity itself? In this video, we will journey through the mysteries of this astronomical giant, exploring its formation, its impact on the surrounding galaxy, and the groundbreaking discoveries it has yet to reveal. Prepare to venture into the unknown, where the boundaries of science and imagination collide, and the story of TON 618 awaits. TON 618 is so far away that the light we receive from it began its journey over 10 billion years ago. This means we are looking into a past where the universe was still young, a mere third of its current age. And in that early, chaotic cosmos, TON 618 already existed as a blazing quasar, its host galaxy glowing brighter than entire clusters due to the phenomenal energy unleashed by matter spiraling into this supermassive black hole. But what truly stuns astronomers is not just its luminosity or distance, it's the scale. The Schwarzschild radius, or event horizon, of TON 618 is so vast that it could engulf the entire solar system hundreds of times over. If we replaced our Sun with TON 618, its event horizon would extend well beyond the orbit of Pluto. We are talking about a black hole so large, it defies classification and challenges our understanding of how such objects form and evolve. TON 618 wasn't discovered in a dramatic burst of data, nor did it reveal itself suddenly to the world of astronomy. Rather, it was found quietly in the 1950s during a survey of blue stars and quasars. It wasn't until the 1970s that astronomers realized it wasn't a star at all, but a quasar, a bright, active galactic nucleus powered by a supermassive black hole. It was only in 2004 that a team led by astronomer C.M. Urey analyzed its spectra and deduced the monstrous mass hiding at its core. What they found left the scientific world stunned. TON 618 was not just an outlier. It was in a category all its own. To understand the implications of TON 618, one must first grasp what a black hole is, and especially what a supermassive black hole entails. A black hole is a region in space where gravity is so intense that nothing, not even light, can escape from it. This leads to the concept of the event horizon, the boundary beyond which escape becomes impossible. The more mass a black hole has, the larger this event horizon becomes. At stellar mass scales, black holes are created from the deaths of massive stars. But supermassive black holes like TON 618 reside at the centers of galaxies, and their formation is still one of the greatest mysteries in astrophysics. TON 618 doesn't just bend the rules. It practically shatters them. How could something of such incredible mass have formed so early in the universe's history? Traditional models of black hole growth suggest that even with constant, Eddington-limited accretion, the theoretical maximum rate at which a black hole can consume matter without blowing itself apart with radiation pressure, it would take billions of years to reach the mass of TON 618. But we observed TON 618 as it was just 3 billion years after the Big Bang. Something doesn't add up. This has led scientists to hypothesize alternative pathways for rapid black hole growth. Could there be massive seed black holes forming from direct collapse of gas clouds, bypassing the stellar phase entirely? Could early black holes have experienced short bursts of super Eddington accretion, gobbling up mass at rates once thought impossible? The implications are enormous. TON 618 acts as a cosmic probe into the infancy of structure formation in the universe. If such giants existed so early, then our understanding of galaxy formation, dark matter dynamics, and the evolution of large-scale structures needs revision. TON 618 could be the key to uncovering these cosmic secrets. It also challenges our models of black hole host galaxy coevolution. In the modern universe, there's a well-established correlation between the mass of a galaxy's central black hole and the properties of its host galaxy's bulge, the so-called M-sigma relation. But TON 618 may be so massive that it violates this relation entirely. Was its host galaxy equally enormous, possibly one of the earliest and largest galaxies ever formed? Or did TON 618 somehow outgrow its environment, becoming a galactic parasite instead of a partner? And then there's the light. Quasars like TON 618 shine with the brilliance of thousands of galaxies. This isn't due to the black hole itself, but the accretion disk, a swirling maelstrom of superheated gas and dust spiraling into the black hole at nearly the speed of light. As matter is compressed and heated by gravitational forces and friction, it emits radiation across the electromagnetic spectrum. TON 618's quasar is visible from over 10 billion light-years away because of this light. The very thing that is being consumed emits a final, defiant blaze before it crosses the point of no return. In a very real sense, the light of TON 618 is a funeral pyre for the matter it devours. This extreme brightness has allowed astronomers to study TON 618 in considerable detail. Spectroscopic analysis reveals the elemental composition of the accreting material, the speed at which it's moving, and the gravitational redshift induced by the immense curvature of spacetime near the event horizon. These measurements are then used to estimate the black hole's mass. And every time, the number comes back staggeringly high, over 66 billion solar masses. To put that into perspective, the supermassive black hole at the center of the Milky Way, Sagittarius A, is about 4 million solar masses. M87, the famous black hole imaged by the Event Horizon Telescope, weighs in at around 6.5 billion solar masses. TON 618? It's 10 times that, and then some. But TON 618 isn't just notable for what it is. It's also notable for what it might represent. Could there be more such giants lurking at the edges of the observable universe? Are there hypermassive black holes that surpass even TON 618 in mass, hidden behind veils of cosmic dust or lying dormant and dark? Our current instruments may simply be unable to detect them yet. TON 618 might be the tip of a very large, very dark iceberg. Studying TON 618 also raises philosophical questions. Black holes are often seen as endpoints, as destroyers, but they are also creators of structure. Their gravitational pull shapes galaxies, regulates star formation, and seeds the scaffolding of the universe. Could TON 618 have influenced the formation of an entire galactic supercluster? Could its gravity have acted as a cosmic shepherd, pulling matter together in the early universe? Even time itself becomes strange near such a black hole. General relativity tells us that time slows down in strong gravitational fields, a phenomenon known as gravitational time dilation. For an observer hovering just outside the event horizon of TON 618, time would pass dramatically slower relative to someone on Earth. Theoretically, a second near the event horizon could equate to millennia or more in the universe beyond. In that sense, TON 618 is a natural time machine, not for traveling through time, but for freezing it. And what lies beyond the event horizon? This question has haunted physicists for over a century. Inside, our known laws of physics break down. General relativity predicts a singularity, a point of infinite density and zero volume. But quantum mechanics rejects this notion. The truth likely lies in a theory of quantum gravity, a still elusive unification of Einstein's and Heisenberg's visions. TON 618, by its sheer scale, may offer clues toward this unification. If we can model its interior mathematically, or probe its behavior with future instruments, we may finally reconcile these two great pillars of modern physics. But perhaps most awe-inspiring is simply the idea that TON 618 exists. That something so vast, so ancient, and so powerful still shines across the gulf of time to reach us here, on this tiny blue world. In the scale of the cosmos, we are infinitesimal, but we are capable of perceiving giants. We are capable of all. And this is just the beginning of our journey into TON 618, the dark, distant colossus that guards the secrets of creation itself. This supermassive behemoth, TON 618, not only stretches the limits of mass but also challenges the very frameworks through which we understand galactic and cosmic development. It serves as a dark beacon of extremity, a gravitational tyrant reigning over the edge of comprehension, and yet, its existence is backed by data, measurements, and signals carried across billions of years. Its presence was first inferred not through traditional stargazing, but by carefully analyzing the optical spectrum of light it emits, light that took over 10 billion years to reach Earth. Now, when we talk about black holes emitting light, it's important to clarify, black holes themselves do not emit light. Their gravity is so immense that not even photons, the fundamental particles of light, can escape their event horizon. But TON 618 is not just a black hole. It is an active galactic nucleus, a quasar, a titanic structure surrounded by an accretion disk of matter spiraling at relativistic speeds. This disk heats up due to immense friction and gravitational compression, radiating light and energy on a scale that defies terrestrial imagination. It is this light, these specific signatures in the electromagnetic spectrum, that revealed the hidden monster within. Using spectroscopy, astronomers discovered broadened emission lines, essentially, lines in the light spectrum that had been smeared due to Doppler effects. These lines indicated that the gas clouds swirling around TON 618 were moving at millions of kilometers per hour, a staggering speed that could only be explained if they were caught in the gravity of something incredibly massive. This alone would be enough to make TON 618 a worthy subject of cosmic fascination. But the rabbit hole goes deeper. Much deeper. Because TON 618's mass is estimated at an almost unthinkable 66 billion solar masses. To grasp the weight of this statement, consider this: our Sun is approximately 1.989 times 10 superscript 3 kilograms. TON 618, then, is 66 billion times that. That is a 66 followed by 9 zeros. It's not merely massive, it borders on incomprehensible. If TON 618 were placed at the center of our galaxy, it would engulf not just the Milky Way's core, but potentially distort the entire structure of the galactic disk itself. So, how did it get so massive? This is one of the greatest puzzles in astrophysics. The universe, by our best estimations, is about 13.8 billion years old. TON 618's light has traveled for over 10 billion years, which means this black hole formed in the very early universe, just a few billion years after the Big Bang. This gives rise to a cosmic conundrum. How did something so massive form so quickly? Traditional models of black hole formations suggest that they begin as the collapsed cores of massive stars. These stellar black holes might be a few tens of solar masses. Over time, through processes like accretion, matter falling into the black hole, and mergers, colliding with other black holes, they can grow. But this process is not fast. It's constrained by what's called the Eddington limit, a balance between the gravitational pull drawing matter inward and the radiation pressure pushing it away. If a black hole accretes matter too quickly, the radiation produced by this matter heats up and pushes other material away, essentially choking off its food supply. TON 618 seems to break this rule. For it to become so massive in just a few billion years, it would have had to grow continuously at or near the Eddington limit, or even find a way to bypass it. This has led to a number of theoretical models. Some suggest that TON 618 may have been born from direct collapse, a process where a massive gas cloud in the early universe skips star formation and collapses straight into a black hole of tens of thousands, or even hundreds of thousands of solar masses. These so-called seed black holes would give it a huge head start. Others propose super-Eddington accretion, where the black hole temporarily feeds at a rate far beyond the normal limit. This might be possible if the surrounding matter is extremely dense and collapses rapidly, or if angular momentum is efficiently dissipated. There is even speculation that certain black holes may have grown through dark matter interactions, though this remains highly theoretical. Beyond its formation, TON 618 invites questions about the limits of cosmic structure. If black holes can become this large, could there be larger ones still undetected? Is there a natural cap on their growth? Could an even larger black hole be lurking in the darkness, evading detection because it is not an active quasar? After all, the universe is vast beyond measure, and our telescopic eyes can only peer so far. Ton 618 also forces us to confront the implications of scale. It's so large that its Schwarzschild radius, the distance from its center to the event horizon, is more than 195 billion kilometers, or about 29,000 times the radius of the Sun. For comparison, the distance from Earth to Pluto is around 7.5 billion kilometers. That means TON 618's event horizon is nearly 26 times that entire span. This makes it not just a point in space, but an entire region, a cosmic domain in its own right. The gravitational pull of TON 618 is so immense that even light from its accretion disk is distorted, bent, and stretched by its influence. If you were to somehow orbit the black hole, hypothetically, of course, you would witness light from background galaxies twisted into rings and arcs, known as Einstein rings, due to gravitational lensing. Time itself would slow to a crawl near the event horizon, as described by Einstein's general theory of relativity. A few seconds near the edge of TON 618 could correspond to years, even centuries, in distant space. This black hole is not located within our Milky Way but is instead situated in a distant galaxy so far away that its light had to cross over 10 billion light-years to reach us. By the time we see it, we are witnessing TON 618 as it existed in the distant past. It may no longer exist in the form we observe. It might have merged, changed, or even entered a dormant state, but we will not know for billions of years. Its luminosity, the amount of energy it emits, is also among the highest known. The quasar formed by TON 618 emits more than 10 to the power of 40 watts. That's a number with 40 zeros after it. It's so bright that, if somehow placed at the center of our own galaxy, it would outshine all the stars in the Milky Way combined, casting shadows on Earth despite being 25,000 light-years away. But luminosity isn't just a spectacle. It's a clue. It allows us to estimate the mass of the black hole using a variety of methods, including the virial method, which measures the velocities of gas orbiting the black hole to infer its gravitational pull. Other methods involve comparing the brightness of the quasar with models of accretion disk behavior. Still, these methods come with caveats. While most astronomers agree on the 66 billion solar mass figure, some estimate its mass could be even higher, possibly exceeding 100 billion solar masses. This would place it into an unofficial class of black holes called ultramassive black holes, as opposed to the more common supermassive ones like Sagittarius A at the center of the Milky Way, which is a mere 4 million solar masses in comparison. The existence of such an enormous black hole challenges our models of galactic evolution. Galaxies and their central black holes are thought to co-evolve. The mass of a central black hole is often closely related to the mass of the galaxy's bulge. But if TON 618 exists, then its host galaxy must have once been unimaginably large and active. Yet TON 618's quasar light appears to overpower any visible light from its host galaxy. Could the galaxy have been devoured or cannibalized during black hole mergers? Could it be that the black hole grew so rapidly that it outpaced the rest of the galaxy's development? These are not questions with simple answers. TON 618 doesn't just exist, it whispers secrets of the early universe, enigmas that astronomers and physicists are still unraveling. Its sheer scale is an affront to simplicity, a cosmic contradiction that seems to say, the universe is bigger, stranger, and more mysterious than you can imagine. And TON 618 is just the beginning. Its gravitational sphere of influence could potentially encompass entire star systems, even dwarf galaxies, drawing them in over eons and tearing them apart as they fall into its accretion disk. When you consider the dynamics of such gravitational dominance, the implications become staggering. This black hole isn't just a passive hole in the universe, it is an active agent of cosmic destruction and transformation. Anything unfortunate enough to drift too close would be caught in a gravitational cascade, accelerated to near light speed, shredded into ionized plasma, and then swallowed into an abyss from which no information can escape. And this leads to one of the most fascinating theoretical discussions of all: what happens inside? General relativity tells us that within the event horizon of a black hole lies a singularity, a point of infinite density where the laws of physics, as we know them cease to function. But quantum mechanics, our other great pillar of modern physics, cannot tolerate this. The conflict between these two frameworks has led to the rise of theories such as quantum gravity, string theory, and loop quantum gravity, all attempting to reconcile these contradictions. Ton 618, by its sheer scale, becomes not only an astronomical object but a battleground of scientific ideology. Theoretical physicists speculate that such immense black holes could even be gateways to other regions of spacetime, or perhaps remnants of primordial structures seeded by fluctuations in the fabric of the early universe. Some suggest that black holes like TON 618 may contain entire universes within them, bubbles of spacetime hidden behind the event horizon. These ideas remain speculative, but the existence of such titanic anomalies forces us to widen our theoretical horizons. What is even more compelling is the fact that TON 618 may represent only a fraction of similar beasts scattered across the cosmos. The reason we know so little about them is due to observational limitations. We only observe quasars when they are active, meaning their black holes are currently feeding on matter. If a supermassive black hole is in a quiescent phase, it becomes nearly invisible, detectable only through indirect methods like stellar motion or gravitational lensing. This means TON 618 might not be unique in its size, just uniquely visible. And visibility, in cosmic terms, is fleeting. TON 618 is visible to us now because we're catching it in a rare phase of galactic evolution. Quasars typically last for only a few 100 million years, a blink in the timescale of the universe. What we are seeing may be TON 618's youthful blaze, a brief outburst of energy before it settles into dormancy. For all we know, in the present moment of our cosmic timeline, TON 618 has long since faded into darkness. Yet the light continues to arrive, carrying with it data about the universe as it was, not as it is. In this way, TON 618 is not just a black hole, it is a messenger. It tells us what the universe was doing when it was still forming stars at an accelerated pace, when galaxies were colliding more frequently, and when dark matter and dark energy had not yet fully settled into the dominant roles they play today. This leads into another critical discussion, the relationship between supermassive black holes and their host galaxies. Observations indicate that the mass of the central black hole is often closely correlated with the velocity dispersion of the stars in the galaxy's bulge, a relationship known as the M-sigma relation. This suggests that black holes and galaxies evolve together, influencing each other through feedback mechanisms involving energy, jets, radiation pressure, and outflows. A black hole like TON 618 would have had profound effects on its surrounding environment, perhaps regulating or even shutting down star formation in its host galaxy. In this feedback model, as the black hole grows, it releases immense amounts of energy. This energy heats up or blows away the gas in the galaxy, preventing it from condensing into new stars. In TON 618's case, its energy output would be so extreme that it could sterilize regions of its galaxy, suppressing galactic development, and reshaping the evolutionary path of the entire system. It is not merely a component of the galaxy, it is its architect, sculptor, and destroyer. From a technological standpoint, observing something like TON 618 requires precision instruments and advanced data analysis. The original discovery came from studying the Sloan Digital Sky Survey data, which maps millions of celestial objects. Quasars stand out in these surveys due to their distinct spectral features, specifically, their strong, broad emission lines. These lines result from the rapid motion of gas around the black hole and provide the redshift necessary to estimate distance. The redshift of TON 618 is about 2.219, placing it more than 10.4 billion light-years away. This also means we are seeing it as it was when the universe was less than 3.3 billion years old. In those early days, the cosmos was still in a state of rapid formation, with matter more densely packed and galaxies colliding frequently. The presence of such a massive black hole at that time period defies the slow, gradual growth models of black hole evolution, pushing us to revise our theories. Some scientists have suggested that black holes like TON 618 could be explained by massive starburst galaxies or frequent black hole mergers in dense protocluster environments. If a galaxy formed in a highly overdense region of the early universe, it may have undergone repeated mergers with other galaxies, each bringing along its own central black hole. These black holes would then spiral toward the center and merge, rapidly increasing the mass of the core object. This hierarchical assembly model could, in theory, lead to an ultramassive black hole relatively quickly. Alternatively, some models explore the idea of primordial black holes, objects formed directly from density fluctuations in the early universe, possibly during the inflationary epoch. If TON 618 began as a primordial black hole, it might have skipped several evolutionary stages, starting off with a massive head start. Though no conclusive evidence exists for primordial black holes yet, their existence could explain many anomalies in cosmological data. TON 618 also compels us to think about the final fate of matter and energy. What happens to the information that falls into such a black hole? According to the no-hair theorem, a black hole is defined only by three parameters: mass, charge, and spin. Everything else, no matter how complex or unique, gets destroyed. This leads to the famous information paradox, a theoretical conflict between quantum mechanics, which states information is never truly lost, and general relativity, which says it disappears forever inside the event horizon. Recent theories, including the holographic principle and the firewall hypothesis, attempt to address this paradox. Some propose that the event horizon acts like a hologram, storing information about the matter that falls in. Others suggest that black holes evaporate via Hawking radiation, slowly releasing information back into the universe. But for a black hole like TON 618, evaporation is not a concern. Its Hawking radiation is negligible compared to its mass, and its lifespan would exceed the age of the universe by many orders of magnitude. It will persist for trillions upon trillions of years, outliving stars, galaxies, and possibly even protons. In the far future, when galaxies have ceased forming and stars have burned out, black holes like TON 618 will remain as the last titanic monuments of a once luminous universe. They will drift through an increasingly empty cosmos, slowly consuming whatever remnants remain, until even they succumb to entropy in the distant heat death of everything. Yet even in this fate, they hold secrets. Black holes remain one of the few places where the laws of physics utterly collapse. If we could one day understand the mechanics of a black hole's singularity, what lies beyond the veil, we might unlock the next great revolution in physics. We might uncover a unified theory of everything, connecting quantum mechanics and gravity at last. And in that quest, TON 618 is more than a black hole, it is a cosmic question mark. Its very existence beckons us forward, pulling at the boundaries of human understanding just as surely as it pulls on the fabric of space. It demands better models, deeper theories, sharper instruments, and bolder imaginations. TON 618 is not just a relic of ancient space, it is a signpost, pointing the way toward deeper truths about the nature of reality itself. In grappling with the enigma that is TON 618, we find ourselves peering into the heart of the most extreme forces the universe can muster. It is not merely a black hole in the traditional sense, but a cosmic phenomenon so immense that it reframes our very understanding of scale, time, and energy. The numbers alone are dizzying. Over 66 billion solar masses compressed into an area where light itself cannot escape. But what do these numbers mean on a truly intuitive level? To comprehend this, we must stretch the imagination. Picture the Sun, the life-giver of Earth, with a gravitational pull so great that it holds our entire solar system in balance. Multiply that single star by a billion, and you approach the mass of some of the largest black holes we've studied. Multiply it again, and again, and again, until you reach 66 billion solar masses. At this point, you are not just comparing masses, you're staring at a gravitational engine powerful enough to influence galaxy clusters. TON 618 has the potential to warp spacetime on a scale that could affect millions of light-years across. This immense size also gives rise to another remarkable aspect, its accretion disk. The accretion disk around TON 618, composed of superheated gas, dust, and stellar debris, spins at incredible speeds as it spirals inward, glowing with such intensity that it outshines its entire host galaxy. This energy is not just impressive, it's one of the most luminous phenomena in the observable universe. The electromagnetic radiation pouring from this disk includes visible light, ultraviolet, X-rays, and even gamma rays, each telling a story about the physics at play near the event horizon. The heat of this disk can reach millions of degrees, driven by friction, magnetic reconnection, and relativistic effects. As matter accelerates and compresses, electrons collide with ions, releasing radiation at an astronomical rate. If we could somehow place TON 618 in the night sky with the naked eye, despite its distance, it would appear brighter than the moon. It emits hundreds of trillions of times more energy than our sun every second. That amount of power is hard to fathom. It's as if a billion Earths worth of nuclear bombs were detonating constantly and simultaneously. But TON 618's impact doesn't end with light. The gravitational pull it exerts means that it warps the very fabric of spacetime itself. Light passing near it bends, forming gravitational lensing effects that can distort and magnify background objects. This effect is useful in astrophysical studies, allowing us to see behind objects and gain new insights into distant regions of space. In extreme cases, black holes can even create Einstein rings, circular illusions caused by warped light paths around the black hole's immense mass. TON 618, given its mass and likely spin, may also be a powerful generator of relativistic jets. These are streams of plasma accelerated to nearly the speed of light and ejected from the poles of the accretion disk. These jets can extend across entire galaxies, disrupting star formation, reshaping galactic evolution, and injecting energy into the intergalactic medium. While direct imaging of jets from TON 618 is beyond current capability due to its distance, its analogues suggest that such activity is probable. There is also the phenomenon of time dilation to consider. According to Einstein's theory of general relativity, time slows down in strong gravitational fields. Near the event horizon of TON 618, time would pass at a dramatically slower rate compared to regions farther away. For an observer hovering just above its edge, seconds could feel like hours or even days in the outside universe. This phenomenon, while theoretical in this context, has practical implications for understanding how matter behaves near such an immense gravitational well. The study of TON 618 also opens the door to discussions on cosmic censorship, a hypothesis which suggests that singularities, points where densities become infinite, are always hidden within event horizons, thus preserving the predictability of spacetime for outside observers. If TON 618 ever underwent a process where its event horizon was disrupted, a theoretical scenario only, it could potentially expose a naked singularity, an object that defies the known laws of physics and invites chaos into our mathematical models. What's also remarkable is the mystery surrounding how TON 618 came to be. Black holes typically grow through two known mechanisms: accretion of matter and mergers with other black holes. The rate of growth through accretion is limited by the Eddington limit, a balance between gravity pulling matter inward and radiation pressure pushing it away. Yet TON 618's mass seems to exceed what traditional Eddington limited growth models allow within the time constraints of the universe's age at the time. This has led some theorists to propose episodes of super Eddington accretion, where matter falls in faster than radiation can resist it. Others believe that the black hole formed from the direct collapse of a massive gas cloud, skipping the star stage entirely. Simulations of early galaxy formation have shown that under the right conditions, such as high gas density, low metallicity, and strong UV radiation, massive gas clouds can collapse directly into black holes with initial masses of tens of thousands or even hundreds of thousands of solar masses. These seed black holes could then grow rapidly during epochs of frequent galaxy mergers. If TON 618 formed from such a mechanism, it may represent a class of ultra-massive black holes that originated from the most extreme environments in the early universe. And yet, for all that we know, TON 618 remains only partially understood. There are still no precise measurements of its spin or detailed observations of its host galaxy. It exists more as a beacon, a puzzle, and a portent than as a fully characterized object. New telescopes, such as the James Webb Space Telescope and future observatories like the Extremely Large Telescope, ELT, will provide higher resolution imaging and more detailed spectroscopy, possibly revealing new information about its environment and structure. Moreover, the existence of TON 618 feeds into the search for even larger black holes. Some theoretical models suggest the existence of stupendously large black holes, slabs, objects that could exceed 100 billion solar masses. These would be even more elusive, possibly too dark or too distant to detect with current instruments. If TON 618 is not the largest, but merely the first of its kind that we've found, the implications are staggering. It would mean that there are other, even greater entities lurking in the dark corners of the cosmos, silent titans that shape the universe from its earliest moments. These possibilities also inspire philosophical and existential questions. TON 618, existing as it did over 10 billion years ago, no longer exists in the same form we observe. It might have continued growing, become dormant, or merge with another black hole to become something even greater. The light we observe now is ancient history, a ghost echo of something vast and unfathomable. The present reality of TON 618 may be entirely different, reminding us of the limits of our knowledge and the strange relationship we have with time and distance. From a human perspective, we are looking across the breadth of the cosmos and seeing an ancient past unfold in real time. We are witnessing the brilliance of a force that was born when life on Earth was still billions of years from forming. In that sense, TON 618 is not just an astronomical object, it is a cosmic memory, a flash of brilliance preserved across time by the very physics that govern light and space. It compels us to ask, what else lies out there, waiting to be seen? If TON 618 could grow to such enormous size in the early universe, what other unknown forces might be at work in shaping the large-scale structure of reality? Could there be black holes that formed even earlier, from even more exotic processes? Might some of these reside in intergalactic voids, quietly consuming mass and shaping gravitational fields in ways we haven't yet measured? The journey to answer these questions begins with observations, continues through theory, and stretches into the realms of the speculative. In many ways, black holes like TON 618 serve the same role in science as mythic monsters once did in ancient cultures, giant, unknowable entities that defined the boundaries of the world and stood as metaphors for the unknown. But unlike myths, TON 618 is real. We can measure its light, chart its effects, and trace its growth. It is not a metaphor, it is a phenomenon. And as we continue to advance in our technologies, simulations, and models, we edge closer to not just describing what it is, but understanding what it means. And as we deepen our exploration into the vast influence and mystique of TON 618, we begin to understand that this ultramassive black hole is not just an isolated curiosity, but a key to unlocking deeper truths about the formation and evolution of the universe itself. Every facet of its being, from its size to its brightness, from its location to its implications, paints a picture of a cosmos far more dynamic and violent than previously imagined. Consider, for instance, the sheer gravitational domain of TON 618. If we could visualize its sphere of influence, known as the gravitational radius or the Schwarzschild radius, it would span billions of kilometers. To put that into perspective, the Schwarzschild radius of our Sun is just under 3 kilometers. A black hole the size of TON 618, with over 66 billion solar masses, would have a Schwarzschild radius measuring more than 1,300 astronomical units, larger than the diameter of our entire solar system by many orders of magnitude. This isn't just a theoretical metric. It represents a region of space where gravity dominates so thoroughly that no object, no light, no information can escape once it crosses the boundary. This kind of immense gravitational field also causes something known as gravitational redshift. As photons of light struggle to escape from the deep gravitational well around TON 618, they lose energy and shift toward longer wavelengths. This redshift becomes a key tool for astrophysicists to measure not only how far the black hole is from us, but how extreme its gravity is. This means that even though the quasar lies over 10 billion light-years away, its gravitational imprint on the light it emits gives us clues about the very curvature of space around it. And then there's the fact that TON 618 is not alone. It is surrounded, most likely, by a host galaxy, which itself might be one of the largest galaxies ever to exist. The black hole at its center would shape the behavior of billions, possibly trillions, of stars. Stars near the galactic core would be whipped around at incomprehensible speeds, pulled by TON 618's gravity, creating dynamic and chaotic environments that can ignite bursts of star formation or rip entire stellar systems apart. These interactions create feedback loops that help sculpt the structure of the host galaxy. This phenomenon, known as AGN, active galactic nucleus feedback, plays a crucial role in how galaxies grow or stop growing. Scientists believe that TON 618 could be part of a larger population of black holes that formed in the early epochs of the universe when matter was more densely packed and galaxies were more prone to collisions and mergers. In such an era, black holes could consume far more material, growing at accelerated rates. Some researchers even hypothesize that ultramassive black holes like TON 618 might be seeds for galaxy clusters, acting as gravitational anchors around which massive structures in the cosmos formed. And this brings us to another cosmic puzzle. How can something so massive have formed so early? TON 618 existed less than 4 billion years after the Big Bang. This is relatively young in cosmic terms, yet its mass rivals or exceeds that of any other known black hole. To accumulate that kind of mass in such a short time defies many of our current growth models. It challenges the limits of accretion theory, calling for periods of super Eddington growth or radically different seed formation scenarios. One idea posits the existence of direct collapse black holes, where a vast cloud of primordial gas bypasses the star phase and collapses directly into a black hole of hundreds of thousands of solar masses. If this were the case with TON 618, then it would have started life already far larger than typical black holes we observe today. That enormous head start would make its current mass more feasible. Another concept involves hierarchical mergers. In the crowded and chaotic young universe, galaxies frequently collided and merged, carrying their central black holes with them. These central black holes would spiral in, radiate gravitational waves, and merge to form larger black holes. If TON 618 is the product of many such mergers, its existence might point to an incredibly turbulent galactic history, one of violent encounters, explosive energy releases, and rapidly forming structures. Meanwhile, TON 618 also forces us to examine the very fabric of spacetime around it. The gravitational field near a black hole distorts time and space, creating a region where our normal intuitions break down. This warping of spacetime is not just a curiosity, it has observable consequences. Light traveling near the event horizon bends, creating the phenomenon of gravitational lensing. If we could observe TON 618 from a distance with perfect clarity, we might see stars and galaxies distorted into arcs and rings, as their light is bent around the black hole's immense gravity. Moreover, TON 618 might be rotating. Most black holes are thought to possess angular momentum, a spin derived from the conservation of the angular momentum of the matter that formed them or was later accreted. A spinning black hole, described by the Kermetric in general relativity, behaves differently from a non-spinning, Schwarzschild black hole. It has an ergosphere, a region outside the event horizon where nothing can remain at rest. Within this ergosphere, space itself is dragged around the black hole at relativistic speeds. This phenomenon, called frame dragging, has potential implications for energy extraction through the Penrose process and could affect the formation and direction of relativistic jets. Jets themselves are another area of intrigue. While we cannot directly observe jets from TON 618 due to its immense distance, the physics of similar quasars and AGNs suggests that they likely exist. These jets are composed of plasma accelerated to near-light speeds and are emitted from the poles of the black hole, perpendicular to the accretion disk. They stretch for hundreds of thousands of light-years and affect star formation far from the black hole itself, regulating the energy balance of the entire galaxy. Such energy emissions are thought to contribute to the cosmic feedback loop, a self-regulating system where a black hole, by accreting matter and emitting energy, actually controls the rate of star formation in its host galaxy. In periods of intense accretion, the quasar can become so bright and energetic that it heats or blows away surrounding gas, halting star formation. Then, as fuel diminishes, the quasar dims, allowing gas to cool and stars to form again. This cyclical process ties the life of a galaxy to the activity of its central black hole, a relationship known as the black hole galaxy coevolution model. And TON 618, by virtue of its enormous size, represents the extreme end of this scale. If we can understand how it interacts with its surroundings, we may uncover universal principles that apply to all galaxies, even our own. Our Milky Way harbors a supermassive black hole called Sagittarius A, but at only around 4 million solar masses, it is dwarfed by TON 618. Yet the laws of physics are the same. TON 618 is simply the most dramatic example. TON 618 also provides a lens through which we can examine fundamental physics. In its gravitational grip, near its event horizon, all known laws of nature converge: quantum mechanics, relativity, thermodynamics. Yet those laws often come into conflict under such extreme conditions. For example, the singularity at the center of a black hole is a point where density becomes infinite, and the curvature of spacetime becomes undefined. General relativity breaks down here, and quantum effects are thought to dominate, yet we have no working theory of quantum gravity to describe it. TON 618, as the most massive known black hole, represents one of the best laboratories for testing the limits of these theories. Some physicists have even speculated that black holes like TON 618 may be gateways to other regions of spacetime, wormholes, or even portals to parallel universes. These ideas remain speculative, but the fact that black holes harbor such possibilities makes them irresistible to researchers. In particular, the theoretical model of the black hole information paradox, posed by Stephen Hawking, suggests that information falling into a black hole might not be lost forever. Could TON 618 hold not just matter, but also the lost history of whatever fell into it billions of years ago? And there's a more poetic perspective. TON 618, with its unimaginable scale and unreachable distance, reminds us of our place in the cosmos. It humbles us, challenges our intellect, and stretches the boundaries of human thought. It is not merely a distant light in the sky, it is a symbol of nature's power and the depth of our ignorance. We have named it, measured it, studied its light, and still we stand in awe. And as the light from TON 618 continues to journey across the vast abyss of space, we find ourselves reflecting not only on what it is, but what it represents: a colossal monument to the ancient universe, a fossilized echo of a time when the cosmos was younger, denser, and more chaotic. Its very existence is a message from the distant past, a whisper of a cosmic epoch filled with violence, intensity, and explosive growth. TON 618 is not merely a black hole, it is a chronicle, a relic, and a riddle. The light we see from TON 618 today began its voyage over 10 billion years ago. At that time, the Earth did not yet exist. The Milky Way galaxy was still forming. There were no humans, no trees, no oceans. The atoms in your body had not yet been forged. And yet that light survived billions of years of cosmic expansion, gravitational distortion, and intergalactic medium, just to end its journey in our instruments. To peer at TON 618 is to look into the time before time, when galaxies were still carving their place into the firmament. And that light, radiated not directly from the black hole, but from the matter swirling around it, gives us a glimpse into a process both destructive and creative. As matter spirals inward toward the event horizon, it accelerates to near light speed. The gravitational forces compress it, heating it to temperatures so high that it emits vast amounts of radiation. These emissions, spanning the electromagnetic spectrum from radio waves to gamma rays, are the signatures of quasars. And TON 618, being one of the most luminous quasars ever discovered, was once among the brightest beacons in the observable universe. But just as fascinating as the light is the darkness. TON 618's event horizon marks the boundary of no return, beyond which all paths lead inward. At this frontier, the escape velocity exceeds the speed of light. Nothing, not even photons, can escape its pull. The event horizon, then, is not a physical surface but a mathematical boundary, one that separates what is knowable from what is forever lost. TON 618's event horizon likely stretches over 1,300 astronomical units, an area so vast it could engulf our entire solar system many times over. And while we cannot observe the event horizon directly due to its immense distance and orientation, we can infer its size and properties from the surrounding emissions. These emissions are chaotic yet structured, shaped by powerful magnetic fields, extreme temperatures, and the angular momentum of the infalling matter. This environment is a natural particle accelerator, where electrons and ions smash together at relativistic speeds, generating radiation in processes far more violent than anything possible on Earth. It's also here that the accretion disk, a swirling platter of gas and dust orbiting the black hole, reigns supreme. This disk is not static but a cauldron of turbulence, shocks, and instabilities. Friction within the disk causes matter to lose energy and spiral inward. Magnetic fields twist and tangle, producing enormous jets that blast material away from the poles at speeds approaching that of light. These jets, in turn, influence intergalactic environments, triggering the collapse of gas clouds into stars or dispersing potential star-forming material entirely. Now one must wonder, what lies at the center of TON 618, beneath the event horizon? Classical general relativity suggests a singularity, a point of infinite density and zero volume. But quantum mechanics refuses to accept infinities. Here lies one of the greatest unsolved problems in physics, reconciling quantum mechanics with general relativity. The core of TON 618 might house not a singularity but something else entirely, a Planck core, or quantum remnant that obeys the laws of a yet undiscovered quantum gravity theory. Some scientists speculate that information falling into TON 618 is not destroyed, as once thought, but encoded on the event horizon itself in a kind of holographic form. This leads to the idea of the holographic principle, the notion that all information contained within a volume of space can be represented on the surface that encloses it. In this view, TON 618's boundary might act like a cosmic ledger, preserving the quantum state of everything it has consumed. It's a concept so alien, so counterintuitive, that it reshapes how we understand space, time, and reality itself. This boundary is also the site of the black hole's entropy, a measure of the amount of information hidden behind the veil of the event horizon. The entropy of TON 618 is mind-bogglingly vast, greater than that of most galaxies. This makes it an important subject of study in black hole thermodynamics, a field pioneered by physicists like Stephen Hawking and Jacob Bekenstein. Hawking's discovery that black holes emit radiation, a phenomenon now called Hawking radiation, implies that black holes can evaporate over time. But a black hole the size of TON 618 would take longer than the current age of the universe by many, many orders of magnitude to radiate even a tiny fraction of its mass. This immense longevity grants TON 618 a kind of immortality. Long after the stars have burned out and the galaxies have dimmed, after the universe becomes cold and dark, black holes like TON 618 will remain, silent, eternal monuments to a bygone era. And in the ultimate endgame of the universe, when even these black holes slowly evaporate into nothingness, TON 618 will be among the last lights to fade. The mystery of TON 618 continues to inspire both fascination and scientific inquiry. Is it unique, or merely the first of many such titans yet to be discovered? Could there be black holes even more massive, hidden in the farthest reaches of the universe, their light still traveling toward us? As we develop better instruments, more sensitive telescopes, and more advanced simulations, we may one day find black holes that dwarf even TON 618. Or we may discover that it stands alone at the pinnacle of gravitational might. But its mass, over 66 billion times that of the Sun, is more than just a number. It's a statement about what the universe is capable of. It suggests that under the right conditions, gravity can sculpt structures of such immense scale that they defy human comprehension. And it points to a deeper truth. The cosmos is not only bigger than we think, it is bigger than we can think. This realization leads us into philosophical territory. If the universe can produce an object like TON 618, what else might it harbor? What limits exist in a universe governed by laws that permit the emergence of such extremity? And what does that say about the nature of the cosmos we inhabit, not just as observers, but as participants? The study of TON 618, then, is not merely the study of a black hole. It is a study of the limits of physical law, of the boundaries of knowledge, and of the nature of the universe itself. It is a journey into the deepest, darkest places of reality, where light dies, where time stands still, and where the known ends and the unknowable begins. And yet, even in the seeming finality of that darkness, TON 618 tells us something about beginnings. For a black hole to become this massive, it must have started with conditions that were extraordinarily conducive to rapid and sustained growth. This leads us into one of the most intriguing scientific questions surrounding TON 618. How did it get so big, so fast? Given that the light from TON 618 has taken more than 10 billion years to reach us, and considering its current mass, we are looking at a black hole that must have grown extraordinarily quickly in the early universe. Under conventional models, this kind of growth shouldn't have been possible in the time available. This conundrum has forced astronomers to rethink what they thought they knew about the formation and evolution of supermassive black holes. There are a few prevailing theories that attempt to explain this phenomenon. One possibility is that TON 618 began not as a typical stellar remnant black hole, but as a direct collapse black hole. In this scenario, rather than forming from a supernova, the black hole formed directly from the gravitational collapse of a massive gas cloud in the early universe. These direct collapse black holes could start out with masses ranging from 10,000 to 100,000 times that of the Sun, giving them a significant head start. Another theory suggests that TON 618 may have been the product of multiple black hole mergers. In the chaotic young universe, galaxies frequently collided and merged, and so did the black holes at their centers. These collisions could lead to a rapid compounding of mass, especially if the resulting black hole was embedded in a dense, gas-rich environment where it could continue to feed. And feeding is the operative word. For a black hole to grow, it needs a steady supply of matter. This means that TON 618 likely spent a long period of its early life embedded in an extraordinarily rich galactic nucleus, where it had access to a veritable buffet of gas, dust, stars, and even other black holes. This feeding frenzy would have produced intense radiation, making TON 618 one of the brightest quasars in the universe during its peak. This brightness is not just a spectacle, it's also a tool. Quasars like TON 618 serve as cosmic lighthouses, illuminating the intergalactic medium and allowing astronomers to probe the vast stretches of space between galaxies. The light from TON 618, for instance, can be analyzed for absorption lines, those subtle fingerprints left by gas clouds it passed through on its journey to Earth. These absorption lines tell us about the composition, temperature, and motion of intergalactic matter, turning TON 618 into a probe of the cosmos. But there's a limit to how bright a black hole can shine. This limit is called the Eddington limit, and it represents the point at which the outward pressure of radiation balances the inward pull of gravity. If a black hole tries to consume matter faster than this limit, the resulting radiation would blow away the infalling material, choking off the black hole's growth. TON 618 must have spent an extended period at or near this Eddington limit to reach its current mass, a fact that makes its growth even more impressive. However, recent research suggests that there may be ways to sidestep the Eddington limit, at least temporarily. Certain accretion flows, like those found in slim disk models, allow for super-Eddington accretion. These flows are dense, optically thick, and can trap radiation within them, allowing the black hole to grow faster than previously thought possible. If TON 618 was feeding through one of these mechanisms, it might explain how it became such a behemoth in a relatively short cosmic time frame. Beyond the mechanics of its growth, TON 618 also challenges our understanding of galactic evolution. Supermassive black holes and their host galaxies appear to grow in tandem. There's a correlation, called the M-sigma relation, between the mass of a black hole and the velocity dispersion of stars in its host galaxy. This suggests some kind of feedback mechanism, where the black hole influences the formation and behavior of its galaxy, and vice versa. TON 618, with its extraordinary mass, implies the existence of a titanic host galaxy, one possibly unlike anything we've yet observed. However, due to the extreme distance, we can't resolve the host galaxy directly. But based on the quasar's brightness and spectrum, we can infer that this host galaxy must be massive, active, and filled with material. It may have formed in one of the universe's earliest and largest dark matter halos, drawing in gas from the cosmic web to form a stellar metropolis around a gravitational king. Now, consider the jet emissions associated with quasars. These are often seen shooting out from the poles of the black hole's spin axis, traveling thousands, or even millions of light years into space. Powered by magnetic fields twisted by the rotation of the accretion disk and the black hole itself, these jets can regulate star formation in the galaxy by heating or expelling gas. In this way, TON 618 may have not only shaped the evolution of its host galaxy but also affected nearby galaxies in its cosmic neighborhood, serving as a kind of intergalactic influencer. The power of these jets, and the immense energy TON 618 releases through accretion, places it squarely in the realm of active galactic nuclei, AGN. These phenomena are among the most energetic in the universe, and studying TON 618 helps refine our models of AGN behavior. In simulations, such energy outputs are crucial to solving problems like the cooling flow problem, where galactic gas would otherwise cool too quickly and form stars at rates far higher than observed. The energy from TON 618 likely served as a cosmic thermostat, preventing runaway star formation in its domain. It's worth pausing to appreciate the elegance of this cosmic balance. Black holes like TON 618, though seemingly destructive, are actually sculptors of structure. Their gravity binds galaxies together, their energy output regulates star formation, and their very existence marks the end of some cycles and the beginning of others. They are not just the end points of matter, but pivot points of cosmic evolution. As our instruments and technologies continue to improve, we may one day be able to measure TON 618's spin, a fundamental property that affects everything from jet formation to the efficiency of energy extraction. A spinning black hole can, under the right conditions, allow for the Penrose process or energy extraction via magnetic fields, a mechanism that could make black holes the most efficient energy producers in the universe. Knowing the spin of TON 618 could also offer clues about its history. A rapidly spinning black hole might suggest a history dominated by coherent accretion, matter falling in along-aligned angular momentum vectors. A slowly spinning or chaotic spin axis could imply a history of random, multidirectional accretion events or mergers. These details, subtle as they may seem, are key to unlocking TON 618's past and predicting its future. And what of that future? Barring catastrophic cosmic events, TON 618 is not going anywhere. It will remain anchored in the fabric of its galaxy, growing ever so slowly as it swallows the occasional star, gas cloud, or passing black hole. Its quasar phase may eventually end as it exhausts its nearby supply of matter, becoming quiescent, a sleeping giant, no less dangerous, just less visible. But even then, it remains. Over the eons, it may drift into the outer reaches of its galaxy, or settle at the galactic core, affecting the orbits of trillions of stars through its invisible pull. Eventually, as the universe ages into senescence and most processes wind down, TON 618 will persist as one of the last engines of gravitational interaction in a fading cosmos. And still, TON 618 will endure. Long after the stars have burned out, when galaxies have ceased forming, and when the very atoms that once composed the universe have decayed into subatomic whispers, TON 618 will remain, a silent witness to the universe's final acts. Black holes, as predicted by the farthest reaches of modern cosmology, are among the last celestial structures to persist in the long twilight of existence. Over unimaginable spans of time, trillions of years, TON 618 may slowly evaporate via Hawking radiation, losing mass one particle at a time. But even this process is so slow that it defies comprehension. To evaporate a black hole as massive as TON 618, some 66 billion times the mass of our Sun, would take longer than the current age of the universe multiplied by a number too large to grasp. For all practical purposes, TON 618 is immortal in the context of everything that we know. It will outlast galaxies, stars, nebulae, and light itself. In the cold black silence of the far future, where entropy has claimed the last usable energy and time stretches into meaninglessness, TON 618 will be one of the few remaining testaments that anything ever existed. In this way, TON 618 forces us to confront the ultimate endgame of existence. The physics that govern black holes are, paradoxically, both the most mysterious and the most complete. General relativity, which perfectly describes their gravity, and quantum mechanics, which hints at their deepest paradoxes, collide at the singularity, a point where our current laws of physics cease to apply. TON 618's central singularity is not just a place of infinite density, but a frontier of human understanding. It is a place where space-time curves to its absolute limit, where distance and time lose meaning, where matter is crushed into something beyond form. This singularity, hidden forever behind the event horizon, is the ultimate riddle. It beckons to string theorists, to quantum physicists, to cosmologists and philosophers alike. What lies inside is perhaps unknowable, yet it drives the search for a theory of everything, a unified understanding of all forces and particles. TON 618, enormous and remote, is not just a spectacle of mass and energy. It is a challenge. It dares us to comprehend the fabric of reality itself. The enormity of this black hole also provides a playground for theoretical speculation. What if, some theorists ask, the singularity is not a point but a doorway? Could black holes like TON 618 be portals to other universes, bridges across dimensions? The concept of wormholes, derived from solutions to Einstein's field equations, posits that space could be connected in such a way. Though speculative, it provokes profound thought. TON 618 might not be a dead end but a threshold. Of course, we currently have no observational evidence to support such ideas. But the mere fact that such speculation arises is a testament to the black hole's enigmatic nature. TON 618 represents not just a limit of size, but a limit of knowledge. Back on Earth, the light of TON 618 flickers through the lenses of our most advanced telescopes, carrying information from a universe over 10 billion years younger than our own. The light we see now began its journey before Earth even existed, before the Sun was born, before the Milky Way had fully formed. That light has been traveling through expanding space, redshifted by the universe's growth, stretched and diluted by the passage of time itself. The redshift of TON 618, Z equals 2.219, tells us not just how far away it is, but when its light began traveling. Redshift is the language of cosmic time. Every photon that reaches us from this black hole carries the signature of an earlier universe. Studying it is like looking into a time machine. We see TON 618 not as it is, but as it was, radiant, violent, immense, at a time when the universe was still in its adolescence. This temporal distance creates a strange kind of intimacy. TON 618 is unimaginably far from us, and yet we can know it. We can study its spectrum, measure its mass, infer its energy, and even map the hydrogen clouds that lie between it and us. In doing so, we build a narrative not just of this black hole, but of the universe itself. It's also a story about limits, of perception, of light, of thought. Our instruments can see the faint glow of TON 618's quasar phase, but they cannot pierce the darkness of its interior. Our minds can theorize about what lies beyond the event horizon, but we cannot test those ideas directly. TON 618 is a mirror to our greatest aspirations and our most profound limitations. It stands as a monument to the cosmos and a monument to human curiosity. And let us consider for a moment the human journey that brought us to even discover such a thing. From early stargazers charting the movements of planets with their eyes alone, to Galileo's first crude telescope, to the immense radio dishes and space-based observatories of today, the path to understanding TON 618 spans millennia of intellectual evolution. We have reached out into the darkness with mathematics and machines, and the darkness has answered with things like TON 618, strange, massive, and real. It reminds us that discovery is not just about answers, it's about the deepening of mystery. Each new understanding opens a dozen new questions. What was the original seed of TON 618? What did its host galaxy look like at its peak? How does it continue to evolve now? Is it alone in its scale, or are there others even larger, hidden in the deep cosmic web? Indeed, some simulations suggest that other ultramassive black holes may exist. Black holes with masses over 100 billion suns, perhaps even approaching the theorized upper limits for such objects. But these would be rare, extremely rare, and likely hidden in the centers of the largest, most ancient galaxy clusters. TON 618 might be among the first of this class we have detected, but it may not be the last. To find them, we must peer even deeper into the cosmos. We need new instruments, next-generation observatories like the James Webb Space Telescope, and eventually the 30-meter telescope or the extremely large telescope. These tools may allow us to observe the birthplaces of black holes like TON 618. They may help us uncover the missing link between stellar black holes and the giants that shape galaxies. But more than technology, we need vision. The story of TON 618 is not just about instruments and data. It is about imagination. It is about the human drive to know what lies beyond the next horizon, to comprehend the incomprehensible, to find meaning in the infinite. TON 618 is massive beyond comprehension, but it is not beyond wonder. And wonder is the first step toward knowledge. Its sheer gravitational might is more than a number. It is a profound illustration of nature's power to sculpt extremes. TON 618 is not merely large, it is grotesquely immense. The event horizon of this black hole, the invisible boundary beyond which nothing escapes, spans a diameter that may exceed 400 billion kilometers. That's more than 60 times the diameter of our entire solar system. Imagine the Sun at the center, and the outermost boundary of TON 618 stretching thousands of times farther than Pluto's orbit. So far, in fact, that light itself would take days to traverse the distance from edge to edge. Everything inside this vast sphere is lost forever, consumed by the singularity. And yet, outside this boundary lies a dance of destruction. Material spiraling toward the event horizon doesn't fall silently. It heats up, collides, compresses, and emits radiation, a process that produces the blazing light of the quasar we observe. In TON 618's case, the accretion disk is one of the brightest sources of light in the known universe. It blazes with the radiance of hundreds of trillions of suns, outshining entire galaxies and painting the cosmos with its searing blue-white glare. This blinding brilliance also allows us to peer into its secrets. By studying the light emitted from the accretion disk, scientists can calculate its velocity, determine the composition of the falling matter, and even estimate the black hole's spin. While TON 618's spin remains uncertain, some models suggest it could be rotating at nearly the speed of light. This rotation twists spacetime itself, dragging nearby matter into tight spirals and accelerating jets of particles outward in opposite directions. These jets, if they exist in TON 618's case, may span millions of light years, punctuating the cosmos with high-energy beams that can heat intergalactic gas and influence the formation of surrounding galaxies. Such feedback mechanisms are central to our modern understanding of galaxy evolution. TON 618 isn't just a passive consumer of matter, it's an active agent shaping its cosmic neighborhood. This is a key insight. Once, astronomers believed that black holes were merely endpoints of stellar life cycles. Today, we know they are architects of cosmic structure. Without the influence of supermassive black holes, galaxies might never have formed into the elegant spirals or massive ellipticals we see across the sky. The energy released by accretion can trigger or suppress star formation, regulate the growth of galaxies, and maintain the thermal balance of entire galactic clusters. TON 618, therefore, is not just a curiosity, it's a linchpin in the grand design of the universe. Its influence may span not just hundreds of thousands of light years, but potentially billions. And though we see it as it was 10 billion years ago, its legacy could still be unfolding in ways we cannot yet perceive. The enormity of such a role can be difficult to process. Human brains are not wired to understand cosmic proportions. Our lifespans, our senses, our daily experiences are anchored to a tiny scale. But TON 618 demands that we think bigger. It forces us to stretch our imaginations across epochs and parsecs, to visualize energy outputs greater than entire star clusters, and to grasp gravity so strong that it rewrites the rules of space and time. And yet there's still something poetic in our connection to this monster. The atoms in our bodies, carbon, oxygen, nitrogen, were forged in stars that once burned billions of years ago. Those stars themselves were shaped by the galaxies they inhabited, and those galaxies, in turn, were influenced by the black holes at their centers. TON 618 may lie at the other end of the universe, but in a strange, cosmic way, its existence is part of our story too. We are made of stardust, and stardust is shaped by black holes. It is humbling to realize that, from our little planet orbiting an average star in an average galaxy, we can point our instruments into the night sky and glimpse this colossal entity. That we can measure its light, decode its mass, theorize its formation, and debate its implications. The gap between human scale and cosmic scale is vast, but knowledge is the bridge. Curiosity is the fuel. And black holes like TON 618 are the ultimate destinations. They are the testing grounds for our theories. General relativity describes how gravity works on the large scale. Quantum mechanics governs the tiny scale of particles. Black holes, and especially supermassive ones, sit at the intersection. They are the arenas where both must be true, and yet, where both appear to break down. The singularity at the heart of TON 618, for all its mass, is still hidden behind an event horizon, where current physics can only speculate. The quest to understand what lies beyond that veil has given rise to some of the most ambitious ideas in science. Some believe quantum gravity will replace our current models, uniting general relativity with quantum mechanics into a single theory that explains everything from black hole cores to the birth of the universe. Others explore the idea that information, once thought to be destroyed in black holes, is preserved, perhaps encoded in the event horizon itself in a kind of cosmic hologram. This holographic principle suggests that everything we observe inside the black hole could be represented as data on its surface. If true, TON 618 might not only be a physical object, it might be an information vault, encoding the history of everything that has ever fallen into it. Stars, planets, gas, dust, light, each has left its mark on the surface in subtle ways we do not yet understand. The implications are staggering. It would mean the boundary of a black hole is not just a point of no return, it's a storage device for the universe's memory. It would mean the universe itself might operate like a hologram, with three-dimensional phenomena projected from two-dimensional surfaces. In chasing the secrets of TON 618, then, we may not just learn about black holes. We may uncover new truths about the universe itself, its origin, its structure, its fate. We may one day see black holes not as voids, but as engines of information, as fundamental components of a deeper cosmic logic. And still, despite all we know, TON 618 holds its secrets tightly. Its distance makes it difficult to study in detail. Its light is faint compared to closer objects. Its features are masked by intervening gas and dust. But even these challenges inspire innovation. New observational techniques, from interferometry to gravitational wave detection, promise to reveal more than we ever imagined. Gravitational waves, ripples in space-time caused by massive events, offer one exciting frontier. While we haven't yet detected waves from black holes as massive as TON 618, future detectors might. Mergers between ultramassive black holes could shake the very fabric of space. If TON 618 ever collided with a similar black hole, the resulting waves would ripple across the cosmos like the tolling of a bell so deep and low that only the most sensitive instruments could hear. Such a collision would be among the most energetic events in the history of the universe. It would release more energy in a few seconds than all the stars and all the galaxies combined. And it would reshape the surrounding structure of space, perhaps even flinging entire galaxies from their paths. A collision involving TON 618 is unlikely in our frame of reference, but not impossible. In the vast tapestry of cosmic time, anything can happen. And in contemplating the potential of such a collision involving TON 618, we are forced to consider the true volatility of the universe. Nothing is fixed. Nothing is immune to transformation. Galaxies merge, stars die, black holes collide and grow larger. TON 618 is not a static monument, it is part of a dynamic cosmic ballet, moving through spacetime along with everything else, obeying laws we barely grasp. It may have consumed stars, absorbed gas clouds, devoured other black holes. Its mass tells a story of cosmic gluttony, a tale of unstoppable growth over billions of years. But what drives a black hole to grow so large? There are competing theories. One possibility is that TON 618 began life not as a stellar mass black hole, but as a primordial black hole, an object formed shortly after the Big Bang, before stars and galaxies even existed. In that early era, the density of matter was immense, and pockets of gravitational instability may have collapsed directly into black holes of enormous size. If TON 618 is one such relic, then it predates the formation of galaxies, and may have served as a seed around which galaxies themselves coalesced. Another possibility is direct collapse, where massive clouds of primordial gas collapse under gravity directly into supermassive black holes without ever forming stars. This bypasses the slow, steady growth that stellar remnants require. In such a scenario, TON 618 might have formed very early, in a sudden act of gravitational collapse, and then continued growing by swallowing everything in its vicinity. Then there's the merger hypothesis. Black holes grow by colliding with other black holes. In the crowded early universe, galaxy collisions were frequent. Their central black holes would be drawn together by mutual gravity, spiral inwards, and eventually merge. If this happened repeatedly, the resulting black hole could become a behemoth like TON 618. Simulations suggest that after just a few billion years of mergers, such giants could easily exist. And we know mergers are not just theory. The LIGO and Virgo observatories have detected gravitational waves from black hole collisions, proving that these cataclysmic events do occur. Although the black holes observed so far have been much smaller, tens of solar masses, the principle is universal. Massive black holes, given enough time and opportunity, can merge and become even more massive. This opens up fascinating implications. If TON 618 formed through a chain of mergers, then it is not just one black hole, it is many, fused together into a single entity. Its event horizon may be the graveyard of countless cosmic objects, from stars and planets to entire solar systems, all absorbed into one bottomless pit. Yet we must also ask, is there a limit? Can a black hole grow indefinitely? Or is there a natural ceiling? Theoretically, as long as there is material to consume, a black hole can continue to grow. But practical limits do exist. Accretion generates enormous radiation, and that radiation can blow away incoming matter, choking off the black hole's food supply. This self-regulating mechanism, known as the Eddington limit, may explain why even the largest black holes grow more slowly than expected. But TON 618 seems to defy that limit. Its mass suggests it fed at or above the Eddington limit for prolonged periods, possibly due to unusually dense environments or episodic feeding frenzies. In some models, the black hole may have gone through phases of rapid growth, alternating with periods of dormancy. Such behavior is observed in other quasars, which flicker and fade across cosmic timescales. What's truly astonishing is the rate at which TON 618 must have grown. To reach over 66 billion solar masses in just a few billion years, it would need to consume the equivalent of one sun every few years, on average. That's not a quiet meal, it's a continuous cosmic banquet. And every mouthful would emit radiation, carve out shockwaves, and alter the landscape of its host galaxy. Which leads us to the next question. What kind of galaxy could host such a monster? The answer is elusive. TON 618 is so far away, over 10 billion light-years, that its host galaxy is not clearly visible. It is likely that the quasar outshines the galaxy entirely, masking the stars and structure around it. But based on other observations of quasars and their hosts, we can infer that the galaxy surrounding TON 618 is likely enormous, chaotic, and rich in gas. It may be a proto-galaxy, still forming, or it may be the remnant of several merged galaxies, bound together by their mutual attraction to the central black hole. Galaxies like this are rare but not unheard of. In the early universe, conditions were ripe for extreme growth. Gas was plentiful, collisions were frequent, and black holes were eager. Ton 618 may have sat at the crossroads of cosmic filaments, giant streams of matter feeding into the densest regions of space. These filaments are the scaffolding of the cosmic web, and they funnel gas into galaxies like arteries feeding a heart. It's also worth considering that TON 618 might not be unique. It may simply be the most massive black hole we've found so far, not necessarily the most massive that exists. The observable universe contains more than 100 billion galaxies, each potentially harboring a central black hole. Some may rival or even exceed TON 618 in mass, hidden behind dust, obscured by distance, or waiting to be discovered. The quest to find them is ongoing. Future telescopes, like the James Webb Space Telescope and its successors, will peer deeper into the universe than ever before. With higher resolution and broader spectra, they may uncover even more luminous quasars, even more ancient black holes, and perhaps rewrite the record books once again. Ton 618's title may not last forever. Yet even if a larger black hole is found, TON 618's legacy will remain. It was the first of its kind to truly challenge our understanding of cosmic growth. It shattered assumptions, provoked new theories, and opened doors into the most extreme regions of space. It stands as a monument to what the universe can do when left unchecked. It is proof that reality is stranger and grander than fiction. And TON 618 may yet help us answer one of the oldest questions in philosophy and science: what happens at the end? Black holes are not just endpoints of stars. They may be endpoints of information, of space, of time. But are they truly the end? Or are they transitions to something else? Some theories suggest black holes evaporate over time via Hawking radiation, a quantum effect that allows them to slowly lose mass. If true, even TON 618 is not immortal. Given enough time, trillions upon trillions of years, it would fade into nothingness. But others propose more exotic ideas. That black holes may lead to other universes, through wormholes or quantum tunnels. That the singularity is not a dead end, but a passage. In this light, TON 618 could be a gateway. Not a tomb, but a portal. Not an end, but a beginning. And so, TON 618 lingers in our collective imagination not just as a gargantuan object defying comprehension, but as a kind of cosmic question mark. What lies beyond that event horizon? Is it truly a point of no return, or might it be concealing something deeper, more profound? Some of the boldest theoretical physicists speculate that the singularity, the point at the core of a black hole where matter is compressed to infinite density, may not be the end of physical law, but the beginning of new physics entirely. A realm where our current understanding of space, time, and causality no longer applies. Could TON 618 harbor within it the seeds of another universe? This idea, though highly speculative, is a component of certain cosmological models such as those rooted in loop quantum gravity, or the multiverse hypothesis. In these frameworks, black holes might be the birthing points of entirely new universes. Every time a massive star collapses, or when two black holes merge, perhaps something is created, not destroyed. If this is true, TON 618 may have spawned universes so vast that they themselves contain their own galaxies, stars, and perhaps even life. Even more intriguing is the idea of white holes, theoretical opposites of black holes that expel matter rather than consume it. Though no white hole has ever been observed, some hypotheses posit that what enters a black hole might emerge from a white hole elsewhere, possibly in a different region of space or time, or even another universe altogether. TON 618, with its mind-boggling mass and gravitational power, would be a prime candidate for such speculative processes. But these ideas remain on the fringes of mainstream science, primarily because we simply can't observe what happens inside a black hole. The event horizon prevents any information from escaping. Not even light can reveal its secrets. And yet, this very limitation is what makes black holes, and TON 618 in particular, so compelling? They represent the edges of our knowledge. They are the frontiers where physics breaks down, and where philosophy, imagination, and theory must step in to fill the gaps. And if black holes challenge our understanding of space and time, they also provoke deep philosophical questions about causality and determinism. If TON 618 consumes information, as some suggest, then is that information lost forever? Or is it preserved in some form, encoded in the black hole's surface as suggested by the holographic principle? According to this theory, all the information that falls into a black hole is somehow stored on its two-dimensional boundary, rather than being lost in the singularity. This concept, if true, could resolve one of the great paradoxes of modern physics, the information paradox. It would mean that black holes are not the destroyers of knowledge, but rather incredibly complex hard drives, with TON 618 acting as the most massive storage device in the known universe. The implications of this are staggering. If we could somehow decode the information on TON 618's event horizon, we might learn not only what it has consumed, but possibly the history of entire galaxies long since vanished. And this brings us to the observational limitations we face. TON 618 is over 10 billion light-years away, which means we are seeing it as it was 10 billion years ago. It is a window into the past, into a time when the universe was young, chaotic, and violent. We don't know what TON 618 looks like now. In the current era, it might have merged with other black holes, gained or lost mass, or even become dormant. The light from those changes simply hasn't reached us yet. We are forever locked in the past when we observe it, staring at an ancient relic whose current fate remains hidden by time itself. And it's not just distance that limits us, it's technology. While the Sloan Digital Sky Survey was groundbreaking for its time, newer instruments are constantly pushing the boundaries. Radio telescopes, gravitational wave detectors, and next-generation observatories like the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, promise to unlock even more of the cosmic code. These tools may not only discover black holes larger than TON 618 but also reveal more about its structure, its history, and the environment in which it formed. But perhaps even more exciting is the possibility of directly imaging such giants. We've already seen this happen with M87, the supermassive black hole in the center of the Virgo A galaxy. Thanks to the Event Horizon Telescope, EHT, we now have an actual image of its shadow, a stunning achievement that made headlines around the world. One day, we might achieve something similar for TON 618 or its peers, although its extreme distance poses enormous challenges. Yet if we can detect its gravitational influence on surrounding matter, or observe distortions in the cosmic microwave background caused by its ancient activities, we might uncover new clues. These indirect observations can be just as powerful as photographs. Through them, we piece together the life story of TON 618, how it formed, what it devoured, and how it changed the space around it. Speaking of space, TON 618 doesn't merely bend the region immediately around it, it deforms space on a colossal scale. Its gravitational well is unimaginably deep. Anything within hundreds of light-years would feel its pull. Its influence might extend across intergalactic distances, warping the motion of nearby galaxies and distorting the paths of light itself. And that's not just poetic, it's measurable. Gravitational lensing, for example, allows us to detect the mass of invisible objects by observing how they bend light from more distant sources. TON 618 could act as one of the most powerful lenses in the cosmos. These gravitational effects ripple outward, shaping the cosmos in subtle but real ways. Dark matter and dark energy may be the most dominant components of the universe, but black holes like TON 618 provide structure. They are the anchors of galaxies, the engines of quasars, the ghosts of collapsed stars. They are reminders that the universe is not only expanding, it is also collapsing, contracting, and recycling itself through cycles of creation and destruction. In this eternal dance, TON 618 stands as a heavyweight champion, a relic from a time when the universe was forming its first major structures, a witness to cosmic history written in light, gas, and gravity. Its existence raises as many questions as it answers. What else is out there? What forces shape this Leviathan? Could we ever get close to such a giant? Could a civilization survive near it, harnessing its energy or decoding its secrets? Science fiction has long toyed with the idea of civilizations living near black holes, perhaps using them as power sources or even as gateways for time travel. The immense energy emitted by the accretion disk of TON 618 could theoretically power entire star systems. In theory, a Kardashev Type 2 or Type 3 civilization, one that can harness the energy of an entire star or galaxy, might thrive near such an object. It's pure speculation, but one that tickles the imagination. Could black holes be the engines of advanced life? And then there is the haunting possibility that black holes are not anomalies, but endpoints in a universal life cycle. Stars become black holes. Galaxies orbit them. Perhaps even universes collapse into them. And from those collapses, perhaps something else emerges. TON 618, then, is not just an object, it is a symbol. A symbol of cosmic power, mystery, and transformation. The more we learn about it, the more profound our questions become. Its mass is a number, yes, a staggering 66 billion suns. But that number is also a mirror, reflecting our own smallness, our own ignorance, and our insatiable hunger to understand the universe. We peer into the dark, and TON 618 stares back, silent and eternal. And as we continue to reflect on the immensity of TON 618, we realize that it is not simply the size or the age of this black hole that captivates us. It is the implication that the universe is home to such colossal enigmas that still evade comprehension. Even with decades of astrophysical research, even with the most sophisticated models of general relativity, we are still unable to explain with absolute certainty how something of TON 618's magnitude could have formed so early in the universe's timeline. The quasar light we observe from it was emitted when the universe was less than 4 billion years old. This begs the question, how did something that massive form so quickly? One of the prevailing theories points toward the concept of direct collapse black holes. In this model, rather than a black hole forming from the remnants of a single star, an immense cloud of primordial gas collapses directly under its own gravity to form a black hole tens of thousands of times more massive than our Sun, perhaps even more. These direct collapse seeds could then rapidly accrete matter from their surroundings, growing in size at extraordinary rates. If such a seed existed in an exceptionally dense region of the early universe, it could potentially become a supermassive black hole like TON 618 in less than 1 billion years. This theory also introduces an interesting layer to our understanding of cosmic evolution. If direct collapse is a common mechanism in the early universe, it would imply that many supermassive black holes formed this way and that TON 618 is merely one of the most extreme examples. But so far, TON 618 remains uniquely large and luminous, hinting that while the process may be possible, it is not frequently repeated to this scale. Another possibility is that TON 618 achieved its massive size through successive mergers. In the crowded, turbulent environment of the early universe, black holes may have collided and merged much more frequently than they do now. These collisions, especially between already massive black holes, could produce gravitational waves powerful enough to ripple across the cosmos, waves that we are only now beginning to detect through observatories like LIGO and Virgo. A series of such mergers could potentially explain the size of TON 618, although this hypothesis requires finely tuned conditions and repeated events that we've yet to fully verify. This brings us to one of the most profound mysteries in astrophysics, the so-called black hole mass gap. In theory, black holes should fall into two general categories: stellar mass black holes, formed from collapsing stars, and supermassive black holes, found at galactic centers. But in between these, in the range of thousands to hundreds of thousands of solar masses, black holes are surprisingly rare. This gap makes it difficult to understand how one type evolves into the other. TON 618, towering well beyond this intermediate range, challenges us to reconsider the very pathways through which black holes grow. Perhaps it didn't simply grow, it erupted into being, forged in a cosmic crucible under conditions we've yet to replicate or even imagine. The laws of physics, as we know them, do not prohibit such a creation, but they do not predict it easily either. This tension between theory and observation is the engine of scientific discovery. TUN 618 is more than an object, it is a contradiction waiting to be resolved. And with contradiction comes debate. Astrophysicists are divided on the specifics of TUN 618's mass. Since we cannot directly measure a black hole's mass, we rely on indirect methods, primarily the brightness of its accretion disk and the velocity of surrounding matter. These methods are highly sensitive to assumptions, such as the angle at which we observe the quasar, the chemical composition of the surrounding gas, and the exact dynamics of the accretion process. All these introduce margins of error. Some astronomers argue that TUN 618 may be less massive than current estimates suggest, though even conservative figures place it firmly in the uppermost tier of known black holes. This uncertainty has fueled a wave of further investigation. Researchers are now re-examining other known quasars to determine whether we've overlooked similarly massive objects. There's a growing sense that TUN 618 may not be an outlier, but rather the harbinger of a new class of ultra-massive black holes. If this is true, then our cosmic census is incomplete, and we've only begun to scratch the surface of what lies beyond. The search for such titans is further complicated by the fact that quasars, including TUN 618, are transient phenomena. A quasar is not a permanent state, it is a phase in a galaxy's life, when its central black hole is actively feeding on matter. Once the surrounding material is consumed or expelled, the quasar dims, and the black hole enters a dormant phase, becoming virtually invisible. It's possible that many galaxies harbor black holes as massive as TUN 618, but they no longer shine with the intense brilliance that makes quasars detectable. They have become silent giants, lurking in the dark. If we are to uncover these dormant monsters, we'll need to rely on different techniques: gravitational lensing, galaxy dynamics, and the subtle distortions in spacetime that such massive objects induce. These methods are still developing, but they hold the promise of revealing a hidden population of black holes that could reshape our understanding of the universe's architecture. Indeed, the universe itself may be far stranger and more varied than we've ever imagined. The existence of something like TUN 618 suggests a cosmos where extremes are not only possible but perhaps even common. It is a place where the rules bend, where the past echoes through the present, and where the very fabric of reality is shaped by invisible giants. As we press forward, one truth becomes clear: TUN 618 is not the end of the story. It is the beginning. It is the crack in the cosmic curtain that hints at deeper truths, greater mysteries, and unimaginable forces. We look into its depths and see not just a black hole, but a mirror reflecting our own curiosity, our own drive to understand. The questions it raises are not just scientific, they are existential. What is the fate of matter and information? What lies beyond the event horizon? Can space and time be bent to the point of reversal? Can gravity become a doorway rather than a wall? These are questions that stretch our understanding to the breaking point, and then demand that we go further. Because that is what science does. It stares into the dark and says, "Not yet. Not yet do we understand. Not yet do we have the tools. Not yet do we see clearly. But we will. And when we do, we may look back on TUN 618 as the cosmic riddle that led us to a deeper truth." And as we delve even deeper into the enigma of TUN 618, we begin to appreciate the broader tapestry into which it is woven, a cosmos defined not by simplicity, but by overwhelming complexity and staggering scale. Every aspect of this black hole, from its formation and growth to its immense gravitational influence, serves as a case study in the extreme physics that govern our universe. But to truly understand it, we must continue to expand our scope, not only looking at TUN 618 in isolation, but also within the context of cosmic evolution, galactic dynamics, and theoretical models that attempt to stitch together the known and the unknown. Consider the concept of cosmic feedback. This is the idea that the energy emitted by supermassive black holes, including those in the quasar phase like TUN 618, plays a critical role in regulating star formation within their host galaxies. As a black hole consumes matter, The inflow of gas generates immense radiation and energetic outflows, jets, winds, and shock waves, that can heat or blow away the surrounding gas, preventing it from cooling and forming new stars. In this way, black holes like TON 618 act not just as passive eaters of matter, but as active agents shaping the fate of entire galaxies. The feedback from TON 618 must be tremendous. Given the size and brightness of its accretion disk, it's estimated to radiate at or near the Eddington limit, the maximum luminosity a black hole can sustain before radiation pressure counteracts the pull of gravity. This limit is a crucial threshold in astrophysics. If a black hole exceeds it, the surrounding matter can be blown away faster than it can be accreted. TON 618 dancing near this limit implies it is balancing on a razor's edge, consuming as much matter as possible without choking itself off with its own brilliance. And this raises yet another layer of mystery: the efficiency of its accretion. Under the standard thin disk model of accretion, only a certain percentage of the matter falling into a black hole is converted into radiation. But if TON 618 is more efficient than expected, it might be using a different mode of accretion altogether. Perhaps it is tapping into magnetically arrested disk models, or undergoing phases of super-Eddington accretion, temporary periods where the energy output exceeds theoretical predictions. If so, TON 618 could serve as a testing ground for exotic physics in environments that no laboratory on Earth could replicate. Its magnetic fields, for instance, must be unimaginably strong. Magnetic fields are known to play a central role in channeling the inflow of matter, regulating the jet outflows, and influencing the stability of the disk. These fields can become twisted and amplified around the rotating event horizon, creating conditions where plasma is accelerated to relativistic speeds and launched into intergalactic space. The jets emerging from quasars like TON 618 can extend for hundreds of thousands of light years, piercing through the fabric of the galaxy and injecting energy into the intergalactic medium. Imagine, then, the scale of the jets from TON 618. While its exact jet structures have not been directly imaged due to distance and resolution limits, extrapolation from similarly luminous quasars suggests that if it produces jets, and it's highly likely that it does, they could be among the most powerful ever generated in the known universe. These jets would not only heat surrounding gas but might also seed the formation of new galaxies, triggering the collapse of matter in distant regions. The implications are profound. TON 618 may be a cosmic gardener, simultaneously destroying and creating, a paradoxical engine of death and rebirth. It is a reminder that black holes are not merely endpoints in the life cycle of stars, but integral players in the cosmic narrative, influencing structure on scales that dwarf comprehension. The light we see from TON 618 has traveled for over 10 billion years to reach us. That means we are observing it not as it is, but as it was, a snapshot from the distant past. TON 618 could be completely different today. It may have exhausted its fuel, dimmed, and settled into a quiet existence as a dormant black hole. Or it may have continued to grow, becoming even more massive, swallowing stars, planets, even entire star systems in a gravitational embrace that nothing can escape. But this time delay is also a gift. It allows us to look back into the early universe and study conditions that are otherwise inaccessible. TON 618 acts as a time machine, beaming information across eons, telling us not only about itself but about the environment in which it formed, the density of the cosmic web, the distribution of matter, the nature of early galaxies. What's more, TON 618 contributes to our understanding of the cosmic distance ladder. The brightness of quasars, when calibrated properly, can be used as standard candles, objects whose intrinsic brightness is known and can therefore be used to measure distance. This technique is still being refined, but with more objects like TON 618, we may one day use quasars to map the structure of the universe on unprecedented scales. There is also a growing movement in theoretical physics to explore the possibility that black holes like TON 618 could offer insights into quantum gravity, the elusive theory that would unify general relativity with quantum mechanics. The event horizon, the boundary beyond which nothing can escape, is a place where classical physics breaks down. Inside, the singularity, an infinitesimal point of infinite density, challenges the very fabric of known physics. Some theories, such as loop quantum gravity and string theory, propose that singularities are replaced by exotic structures, quantum foam, or compactified dimensions. Others suggest that black holes are not singularities at all, but gateways to other universes, wormholes or Einstein-Rosen bridges. Could TON 618, in its unimaginable size, be a cosmic portal, a passage to elsewhere? This is pure speculation for now, but it is not science fiction. It is a logical consequence of equations taken to their limits. Even more provocative is the idea of black hole cosmology, the hypothesis that our universe itself may be the interior of a black hole in another universe. In this model, the Big Bang was not the beginning of everything, but the formation of a white hole, the inverse of a black hole, spewing matter into a new, expanding realm. If so, then perhaps TON 618 is not just a massive object. It is a universe in gestation, its own cosmos waiting to be born. Of course, these are frontiers of thought, teetering on the edge of verifiability. But the beauty of science lies in this daring. We do not stop at what is known, we reach beyond, guided by data, but driven by wonder. And TON 618, in all its enormity, continues to be a muse for that wonder. It beckons astronomers, physicists, and dreamers alike. It challenges our models, rewrites our assumptions, and stands as a cosmic sentinel, silent, ancient, powerful. As telescopes grow more sensitive, like the James Webb Space Telescope, and future projects like the 30-meter telescope, the extremely large telescope, and the square-kilometer array, we will peer deeper into space and further into time. We will search for more objects like TON 618, map their environments, analyze their spectra, and decode their stories. But even if we never find another quite like it, even if TON 618 is truly unique, it will remain one of the greatest cosmic revelations of our age. It will remind us that the universe is still wild, still filled with mysteries, and still capable of humbling us with its grandeur. And as we keep exploring the ever-deepening enigma of TON 618, we find ourselves questioning not only the physics of its being, but also the very philosophical framework within which we interpret such cosmic monstrosities. The size of TON 618 is not merely a number. It is a challenge to our understanding of cosmic time, structure, and even our place in the universe. To grasp what 66 billion solar masses truly means is to stretch the limits of human comprehension to their breaking point. Let's pause for a moment and truly visualize this. If our Sun, a relatively average star, were the size of a standard beach ball, TON 618 would be a gargantuan object so large that if it were scaled proportionally, it would stretch across multiple cities. And this is not just a metaphor. The event horizon, or Schwarzschild radius, of TON 618 is estimated to be around 1,300 astronomical units in diameter. 1 astronomical unit is the average distance from the Earth to the Sun. That means the edge of TON 618's event horizon could engulf our entire solar system many times over. Not just Earth. Not just the outer planets. The entire orbital range of the most distant comets in the Oort cloud could fit within its boundary. It's not a black hole, it's a cosmic abyss. But size alone isn't the only impressive thing about it. What's even more compelling is the energy, the structure, and the balance TON 618 maintains in the hostile, chaotic environment of a quasar. The radiation spilling from the material orbiting this black hole would be enough to strip atoms, sterilize regions of space, and perhaps even impact the chemical structure of intergalactic gas across millions of light-years. The fact that this power source is gravitational in nature, a result of matter falling into a singularity, is a poetic twist of the universe's fundamental rules. Gravity, the weakest of the 4 known fundamental forces, becomes the most powerful engine when condensed into the geometry of a black hole. Now, let's look even closer at the quasar structure. A quasar, short for quasi-stellar radio source, appears star-like in basic optical telescopes, but radiates more energy than a trillion suns. In the case of TON 618, its luminosity has been estimated at over 10 to the power of 40 watts, completely dwarfing our Sun's output of about 3.8 times 10 to the power of 26 watts. This difference is not merely exponential. It's dimensional. You could multiply the Sun's output by trillions, and still fall short of the monster that is TON 618. This energy is not coming from fusion, like it does in stars, but from the efficient conversion of gravitational potential energy into radiation via friction and magnetohydrodynamic processes within the accretion disk. Matter falling toward the event horizon accelerates to near light speeds, becomes compressed and heated, and emits incredible quantities of light and high-energy radiation. The disk itself could span light years in diameter, spinning at relativistic velocities and generating magnetic storms of ferocious intensity. Clumps of matter may form and collapse, turbulent eddies may rise and dissipate, and powerful shocks may ripple across the disk as gravitational waves echo through its structure. In this environment, electrons are torn from atoms, and plasmas swirl in chaotic patterns guided by both magnetic and relativistic effects. This isn't just extreme physics, it's physics in a state of pure violence, ordered only by the underlying symmetries of space-time itself. The observational side of TON 618 is just as captivating. We've never imaged it directly, and likely won't for many decades. But through spectroscopic analysis, redshift measurements, and careful comparison with other quasars, we've pieced together its nature. The light from TON 618 has traveled 10.8 billion years to reach Earth. In that time, the universe itself has expanded, stretching the wavelengths of light emitted by the quasar. This cosmological redshift not only informs us of TON 618's age, but also tells us about the expansion rate of the universe itself. In this way, TON 618 becomes both an object and a measuring stick, an ancient lighthouse whose light encodes the fingerprints of spacetime. Its classification as a hyperluminous quasar places it in the highest tier of brightness observed in the cosmos. This hyperluminosity is a double-edged sword. It makes the quasar visible across immense distances, but it also oversaturates the surrounding region with radiation, often masking details we'd like to observe more clearly. This creates a paradox. The very property that allows us to detect TON 618 is also what prevents us from understanding it fully. And yet, as our observational technology improves, so too does our understanding. Instruments like the Very Large Telescope, VLT, the Keck Observatory, and space-based platforms like Hubble and JWST allow us to refine our models. With each new piece of data, each spectroscopic line, each photometric reading, we refine our understanding of TON 618's chemical makeup, its spin rate, its mass accretion behavior, and its likely environment in the early universe. This invites us into another critical domain of black hole science, the connection between a black hole's mass and the mass of its host galaxy. In modern astrophysics, it's generally accepted that a supermassive black hole's mass correlates with the mass of the galaxy's bulge, a relationship known as the M-sigma relation. But TON 618 throws a wrench into this framework. Its mass is so colossal that it suggests either a galaxy far more massive than we've observed or an alternate evolutionary track entirely. Could TON 618 be a primordial object? Some hypotheses suggest that certain supermassive black holes form not through the slow accumulation of matter over billions of years, but through direct collapse in the early universe. These black holes may have formed from massive gas clouds that skipped the star formation phase entirely, collapsing directly under their own gravity into black holes millions of times the Sun's mass. If TON 618 formed this way, it would provide one of the clearest examples of such exotic formation processes. But it's also possible that TON 618 grew rapidly through a sequence of catastrophic mergers. In this scenario, smaller black holes, perhaps remnants of the first generation of stars or of small galaxies, collided and merged over cosmic time, eventually accumulating into the behemoth we see today. Such mergers would release bursts of gravitational waves, rippling the fabric of spacetime and providing signals that observatories like LIGO and Virgo might detect in the future. This leads us to a breathtaking prospect. What if we could detect gravitational waves from TON 618 or similar systems? Doing so would allow us to peer into the internal dynamics of these monsters, Observe their spins, their orbital alignments, even their histories. The upcoming Laser Interferometer Space Antenna, LISA, is expected to do just that. With a sensitivity tuned to the massive, low-frequency gravitational waves emitted by supermassive black holes, LISA could revolutionize our ability to detect and decode events involving objects like TON 618. Even more speculative is the concept of observing the shadow of TON 618. Just as the Event Horizon Telescope produced the now iconic image of the black hole in M87 one day, perhaps with an interferometric network spanning the solar system, we might achieve the resolution necessary to see the silhouette of TON 618 against its blazing disk. Such a sight would not only be a technological triumph, but a philosophical one, a direct image of the edge of forever. And through all of this, TON 618 remains unchanged, unmoved, unrelenting. It exists as it has for billions of years, massive, dark, and brilliant all at once. It is a paradox, a contradiction, and a monument. And it reminds us that for all our equations and models, the universe is still wilder than we can imagine. It's not merely the size or luminosity of TON 618 that captures the imagination, it's the age-old mystery it embodies. This black hole doesn't just sit silently in the universe, it beckons, like a cosmic siren, pulling us into the depths of questions we can't yet answer. Why does it exist in such a massive state at such an early epoch of the universe? How did it grow so large so quickly? What secrets does it hold about the conditions of the cosmos just a few billion years after the Big Bang? To begin answering these questions, we must delve into the theoretical frameworks that seek to explain black hole formation and evolution. The conventional model suggests that stellar mass black holes, those formed from the collapse of massive stars, gradually accrete material over eons to become supermassive. However, this model breaks down in the face of TON 618. At over 66 billion solar masses, TON 618's existence strains the limits of what conventional accretion can achieve within the age of the universe. In fact, even assuming Eddington-limited growth, which is the theoretical maximum rate at which a black hole can grow while maintaining equilibrium with radiation pressure, TON 618 would still require an enormous head start to reach its current mass by 10.8 billion years ago. This points to a more radical idea: direct collapse black holes. In the chaotic early universe, vast primordial gas clouds may have skipped star formation entirely, and instead collapse directly into black holes with masses of 10 to the power of 4 to 10 to the power of 6 solar masses. These massive seeds would then have a significant advantage, allowing them to quickly outpace their stellar mass cousins in growth. The conditions required for direct collapse are extreme: low metallicity, high inflow rates, and suppression of fragmentation, but not impossible. TON 618 may be the legacy of such a rare and efficient process. And what about its environment? TON 618 is believed to reside in a protocluster region, a forming galaxy cluster in the early universe. Such environments are incredibly dynamic, with frequent mergers and a high density of matter. These conditions would provide TON 618 with a steady influx of gas and possibly other black holes to consume. In fact, if TON 618 resides at the center of such a protocluster, it may play a pivotal role in the evolution of its entire region, influencing star formation rates, gas dynamics, and even the formation of galaxies through powerful feedback mechanisms. This leads us into the heart of one of the most fascinating astrophysical concepts: black hole feedback. As matter accretes onto TON 618, it heats up and emits enormous amounts of radiation. This radiation can in turn heat the surrounding gas, preventing it from cooling and collapsing into stars. It can also drive powerful winds and jets that expel gas from the host galaxy, effectively quenching further star formation. In this way, TON 618 is not just a passive consumer, it's an active sculptor of its cosmic neighborhood. And these jets are not just theoretical. Observations of other quasars and active galactic nuclei, AGN, show relativistic jets extending for hundreds of thousands of light years, powered by magnetic fields twisted by the rotation of the accretion disk. These jets can inject energy into the intergalactic medium, trigger star formation in distant clouds, or strip galaxies of their interstellar medium altogether. Though we have not yet resolved such jets from TON 618, the physics strongly suggests their presence. And if confirmed, they could provide further clues about its spin, a crucial, yet elusive, characteristic of black holes. The spin of a black hole is more than a curiosity. It encodes information about its past. A rapidly spinning black hole likely grew through consistent accretion from a single direction, while a slower or chaotic spin might suggest a history of mergers. Determining the spin of TON 618 could thus tell us whether it grew peacefully through accretion or violently through collisions with other black holes. High spin also means more efficient energy extraction, making the quasar even more luminous. And if TON 618 is spinning near the theoretical maximum, what physicists call an extreme or curved black hole, its ergosphere could in theory allow for exotic phenomena like the Penrose process, in which energy is extracted from the black hole's rotation itself. But let us now consider something even more speculative. What if black holes like TON 618 are more than just cosmic endpoints? Some physicists have proposed that black holes could be portals to other universes or even seeds of new ones. In this framework, the singularity at the heart of TON 618 might not be the end of spacetime, but the beginning of another. Such ideas arise from quantum gravity theories and bounce cosmologies, which suggest that the interior of a black hole could tunnel into a new region of spacetime entirely. While these theories remain unproven, the sheer scale of TON 618 makes it a prime candidate for considering such radical possibilities. And speaking of radical possibilities, there's another theory gaining traction, that ultramassive black holes like TON 618 may not be true black holes at all, but exotic objects known as gravastars or fuzzballs. These hypothetical entities emerge from attempts to reconcile quantum mechanics with general relativity. A gravistar, for instance, would mimic the gravitational effects of a black hole but lack a true event horizon, potentially allowing information to escape and sidestepping the information paradox. The fuzzball model, arising from string theory, suggests that what we perceive as a black hole is actually a tangled mass of strings with no singularity at all. If TON 618 were one of these exotic objects, it could help solve some of the most enduring puzzles in physics. But testing these ideas would require observations of unprecedented precision, tracking subtle differences in gravitational waves, radiation spectra, or even the echoes of matter as it falls toward the event horizon. This brings us to one of the most exciting frontiers in black hole research, the study of quasi-normal modes, the vibrations of spacetime itself as a black hole settles after being perturbed. Detecting such modes from black holes like TON 618 could give us a fingerprint of their true nature. Meanwhile, cosmologists are using TON 618 as a data point in mapping the large-scale structure of the universe. It's not just an object, it's part of the cosmic web, the vast network of filaments and voids that make up the universe's large-scale architecture. By studying its location, its neighbors, and the flow of galaxies around it, researchers hope to refine our models of cosmic evolution, dark matter distribution, and even the elusive force of dark energy. TON 618 also serves as a cautionary reminder of scale. It dwarfs not only stars and galaxies but our own comprehension. Every fact we learn about it pulls on threads that unravel deeper mysteries, about gravity, quantum theory, thermodynamics, and the fundamental nature of reality. It reminds us that the universe is a place of awe-inspiring extremes, and that human knowledge, while powerful, is still a flickering candle in the dark. And perhaps that's the most profound truth TON 618 teaches us. In its darkness, we find light. In its silence, we hear echoes of cosmic truth. And in its terrifying immensity, we are humbled, not diminished, but inspired. As we continue to contemplate the vastness and enigma of TON 618, our thoughts inevitably drift toward the role such a black hole plays in the cosmic timeline, not only as a massive celestial entity, but as a key to understanding the universe's evolution. When we peer into the heart of TON 618, we aren't just looking at an object, we're looking back in time. Because light from this distant quasar has taken billions of years to reach us, observing TON 618 is like looking through a window into the ancient universe, offering a snapshot of cosmic conditions roughly 10.8 billion years ago. That's more than 2/3 of the way back to the Big Bang. It's a time when galaxies were younger, stars were forming at a furious pace, and the universe was a bustling, chaotic arena of growth, collisions, and creation. And yet, even in this formative era, TON 618 had already become a behemoth. That alone compels astronomers to reconsider how we understand black hole formation and growth. The very existence of something so massive, so early, tells us there's more to the story than we once believed. The standard black hole growth model involves accretion, the process by which gas, dust, and even stars spiral into the black hole, releasing energy as they go. The radiation generated by this infall is what lights up quasars like TON 618, making them some of the brightest objects in the universe. But there's a catch. As matter accelerates and heats up in the accretion disk, it produces pressure, radiation pressure, to be precise. This pressure pushes outward, countering the gravitational pull of the black hole. When these forces are in balance, the black hole is said to be accreting at the Eddington limit. The Eddington limit imposes a natural speed limit on how fast a black hole can grow through accretion. Exceed it, and the incoming material gets blown away by the intense radiation. So, if TON 618 adhered to the Eddington limit throughout its life, it must have been born from a seed black hole of unimaginable size, far larger than typical stellar remnants. Alternatively, it might have grown in short, furious bursts of super-Eddington accretion, in which chaotic inflows overwhelm radiation pressure for brief periods. These episodes could be triggered by galactic mergers, which funnel gas into the central regions, feeding the black hole in enormous quantities. This leads us into the fascinating realm of galaxy formation and interaction. Galaxies don't form in isolation, they're social structures, constantly interacting, colliding, and cannibalizing one another. During such events, gravitational forces disturb gas reservoirs, sending material plunging toward galactic centers. If TON 618 resides in a galaxy that underwent several of these major mergers early in its life, it could have received massive infusions of gas and possibly even other black holes, compounding its mass in a cosmic feeding frenzy. But with that mass comes power and responsibility. Black holes of TON 618 scale aren't just massive, they're transformative. Their influence extends far beyond their event horizon. The radiation they emit, the winds they drive, the jets they launch, all of these can have profound effects on their host galaxies. These feedback mechanisms can regulate star formation, suppress galactic growth, and even alter the chemical makeup of surrounding interstellar and intergalactic matter. This regulatory role is more than theoretical. Observations of galaxies both near and far reveal signs of this feedback at work. Cavities carved into hot gas, jets spearing through galactic halos, and vast outflows of material moving at thousands of kilometers per second. TON 618, with its monstrous output, likely shaped its environment in similar ways, curbing further star formation and reshaping the galactic ecosystem in its vicinity. And speaking of output, it's worth considering just how luminous TON 618 really is. With a bolometric luminosity estimated to be over 10 to the power of 41 watts, it outshines entire galaxies. In fact, it emits more energy every second than all the stars in the Milky Way combined. This mind-boggling output arises from the intense friction and heating within its accretion disk, where material moves at relativistic speeds before crossing the event horizon. Let's take a moment to describe what's actually happening in that accretion disk. Picture a swirling vortex of incandescent plasma, spiraling in tighter and tighter circles. As it nears the black hole, the material heats up to millions of degrees, emitting copious amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays. Magnetic fields whip through the disk, creating turbulence and possibly driving the formation of relativistic jets, narrow beams of charged particles ejected at near-light speeds from the poles of the black hole. These jets, if present in TON 618, could stretch across thousands of light-years, punching through galactic halos and spilling into intergalactic space. They would be visible in radio frequencies, acting as cosmic beacons to observers on Earth. The alignment of such jets relative to our line of sight could even influence how we perceive TON 618, whether we see it as a blinding quasar, a radio-loud active galaxy, or something else entirely. And here lies another mystery. Our observations of TON 618 are still limited. Unlike nearby black holes, we can't resolve its structure or track individual features in real time. What we see is the integrated light from a distant source, a quasar glowing from nearly 11 billion light-years away. But with next-generation telescopes like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, we may one day peer deeper, with finer resolution and broader wavelength coverage, into the heart of this quasar. These instruments could help disentangle the components of TON 618's environment, revealing clues about its host galaxy, accretion disk, and surrounding gas. We may even begin to map the movement of gas clouds near the event horizon, using techniques like reverberation mapping. This method tracks the time delay between variations in the continuum light from the accretion disk and the response of emission lines from gas clouds nearby. By studying these delays, astronomers can infer the geometry and scale of the broadline region, a key to estimating the black hole's mass more precisely. And the mass? Oh, the mass. TON 618's estimated 66 billion solar masses place it near the theoretical upper limit of black hole mass in our current models. Some theorists propose that there is a cap, perhaps around 100 billion solar masses, beyond which black holes can't grow, due to limited accretion fuel and destabilizing feedback. If that's true, TON 618 is brushing up against the ceiling of cosmic possibility. But if new observations reveal an even larger mass, we may have to revise that ceiling, or throw it out altogether. Of course, measuring the mass of such a distant black hole is no small feat. It relies on indirect methods, primarily the analysis of emission lines in the quasar's spectrum. These lines, such as those from ionized magnesium, Mg2, or hydrogen, H-beta, are broadened by the Doppler effect as gas moves rapidly around the black hole. By combining the width of these lines with the luminosity of the quasar, astronomers can estimate the size of the broadline region and thus derive the black hole's mass using virial equations. But even these estimates carry uncertainties. The geometry of the gas clouds, the inclination of the disk, and the presence of outflows can all skew the results. That's why multiple lines and models are often used to cross-check estimates. And with each new measurement, we edge closer to understanding whether TON 618 is an outlier, a harbinger, or something altogether beyond our current frameworks. Its very existence challenges the conventional boundaries we've placed on black hole formation, galactic evolution, and the life cycle of quasars. TON 618 looms at the edge of what we think is cosmically possible. And yet it exists, not just as a mathematical model or simulation, but as a real, physical object emitting photons that we can detect and analyze. It is a testament to the universe's ability to confound, surprise, and humble us. Every data point associated with TON 618 pushes us to ask deeper, more difficult questions. How did it grow so fast? What kind of galaxy could contain such a monster? Is it still growing, or has it reached a plateau? Could even larger black holes be lurking beyond the cosmic horizon, waiting to be discovered? To answer these questions, scientists turn to the universe's infancy, the era known as the Epoch of Reionization. This period, occurring roughly 400 million to 1 billion years after the Big Bang, marked the first light emerging from the darkness that followed cosmic inflation. It's in this era that the earliest stars, galaxies, and black holes began to form, reshaping the universe from a featureless sea of hydrogen into a complex web of light and matter. For TON 618 to have become so massive by just a few billion years after this epoch, its growth must have started astonishingly early, possibly from black hole seeds that were themselves far larger than the remnants of the first stars. This speculation brings us into the frontier of cosmological research, the possibility of direct collapse black holes. Unlike the black holes that form from supernovae, typically with masses between 10 and 100 solar masses, direct collapse black holes are hypothesized to form from the collapse of massive gas clouds in the early universe, bypassing the star stage entirely. Under the right conditions, such a collapse could yield seed black holes with masses between 10,000 and 1 million solar masses, more than sufficient to explain the rapid formation of supermassive black holes like TON 618. The catch, of course, is that direct collapse requires a finely tuned environment, low metallicity, high inflow rates, and the suppression of fragmentation that would otherwise lead to star formation. Whether such conditions were common enough in the early universe to account for the number of known quasars remains a matter of intense debate. Nevertheless, simulations suggest that under specific scenarios, such as strong ultraviolet radiation fields inhibiting molecular hydrogen formation, these conditions could have occurred with sufficient frequency to spawn a population of early, massive black holes. From a theoretical standpoint, TON 618 is a natural testing ground for these ideas. It anchors one end of the black hole mass spectrum, providing an extreme data point against which models must be calibrated. If our theories can't produce a black hole of its size within the allowed timeframe, then the theories must be incomplete. This is how science progresses, not through certainty, but through failure, iteration, and the relentless push for a better explanation. But TON 618 also holds philosophical weight. The scale of this black hole, its gravitational dominance, its ancient light, its enduring presence across cosmic time, invites us to consider our own place in the universe. As we grapple with its enormity, we're forced to reflect on what it means to exist in a universe that produces such colossal phenomena. We are infinitesimal by comparison, tiny observers on a small planet orbiting a modest star in a nondescript galaxy. And yet, we can detect, measure, and understand something as massive as TON 618. Our minds, though limited in scale, have the capacity to grasp these immense truths, to wrestle with them, to find meaning in them. Indeed, the story of TON 618 is not just about mass and light and gas. It's about discovery. It's about human curiosity pushing against the veil of the unknown. When the Sloan Digital Sky Survey revealed the light from this distant quasar, when astronomers studied its spectrum and inferred its mass, they weren't just cataloging another object. They were opening a new chapter in our understanding of cosmic extremes. That light, the very photons that traveled more than 10 billion years to reach our detectors, originated in a time when Earth didn't exist, when the Milky Way was still forming, when the universe was young and hot and chaotic. It passed through vast voids, through galaxy clusters, through gravitational lensing events and clouds of intergalactic gas, arriving at our telescopes as a whisper from the dawn of time. And in that whisper was encoded a message, that out there, in the dark reaches of the cosmos, lies a black hole so massive that it rewrites what we thought was possible. Let's take a moment to truly appreciate what this means. Black holes, as predicted by Einstein's general theory of relativity, are regions where space-time curvature becomes infinite. They are singularities wrapped in event horizons, boundaries beyond which no information can escape. And while Einstein himself was skeptical of their physical reality, subsequent research has revealed that not only do black holes exist, they are commonplace. From stellar remnants to supermassive giants, they lurk at the hearts of galaxies, fuel the brightest beacons in the universe, and drive cosmic evolution. TON 618 sits atop this hierarchy like a monarch on a cosmic throne. Its gravitational pull extends light years in every direction. Its accretion disk generates torrents of radiation that flood the intergalactic medium. Its very mass warps the geometry of space on a staggering scale. Were you to approach it, a theoretical impossibility, but let's indulge the thought. Tidal forces would tear you apart long before you reach the event horizon. Even light, the fastest thing in the universe, becomes ensnared, spiraling inward and vanishing forever. And yet, we don't need to approach TON 618 to feel its influence. By studying it, by calculating its mass, by modeling its growth, we gain insight into the processes that shape galaxies, that seed structure into the cosmos, that determine the fate of stars and gas and dark matter alike. TON 618 is not just a curiosity, it's a cornerstone of cosmic architecture. Its discovery and study represent a triumph of observational astronomy. The techniques used, spectral line analysis, photometric redshifting, luminosity modeling, are the culmination of decades of research and technological advancement. The telescopes involved, like the Sloan Digital Sky Survey and various radio observatories, are marvels of engineering, designed to sift through the night sky and find needles in cosmic haystacks. The scientists who interpret this data do so with rigor, humility, and a sense of awe. They are mapmakers of the unknown, charting territories where light itself bends and time slows. And they are not finished. TUN 618 may be the most massive black hole currently known, but it likely won't hold that title forever. As observational technology improves, as deeper surveys reach further into space and time, we may find other leviathans, perhaps even larger ones. Each new discovery will refine our models, challenge our assumptions, and deepen our understanding. But TUN 618 will always have a special place. It's a benchmark. A cosmic extreme. A mystery and a marvel rolled into one. It reminds us that the universe is not just vast, it is deeper, stranger, and more magnificent than we can imagine. Its mass, calculated to be over 66 billion times that of our Sun, stretches the limits of astrophysical plausibility. If TUN 618 were to replace the supermassive black hole at the center of our Milky Way, Sagittarius A, its event horizon would engulf not only the orbits of planets like Mercury and Earth but reach far beyond the orbits of Pluto and even some of the Kuiper Belt objects. We are talking about a gravitational radius so large that it would make our solar system look like a microscopic speck swallowed by a gaping cosmic maw. This scale is so far removed from our everyday experience that even metaphors begin to lose their grip. The Schwarzschild radius of TUN 618, the distance from its center to the edge of its event horizon, is estimated to be around 195 billion kilometers. To put that in perspective, light itself would take more than 18 days just to travel across its diameter. This makes it not just a point in space but practically a cosmic structure in and of itself, its own gravitational kingdom, exerting influence on matter and space far beyond its immediate vicinity. But even this enormous size does not fully convey the exotic physics at play. Within the event horizon, all our known laws of physics break down. Space and time switch roles, and all paths inevitably lead inward. No force, no energy, no information can escape. What lies at the core of TUN 618 is unknown, possibly a singularity where density and curvature become infinite, or perhaps something else entirely if quantum gravity has its say. Some physicists propose the existence of Planck-scale structures, exotic matter states, or even new dimensions, but all of this remains speculative. The true power of TUN 618 is in what it represents, a bridge between the known and the unknown. Every quasar, every emission line, every gravitational calculation tied to it is a step into this frontier. And its active nature makes it especially valuable. Unlike dormant black holes, TUN 618 is blazing with energy, actively consuming material, and flooding the cosmos with electromagnetic radiation. This makes it a kind of cosmic lighthouse, its light guiding astronomers through the deep past of the universe. Its discovery in the 1970s as part of a survey of blue stellar objects was initially unremarkable. Back then, TUN 618 was just another faint smudge on photographic plates. But its spectrum revealed something strange. Not only was it incredibly luminous, but its redshift indicated a staggering distance, more than 10 billion light-years away. The implication was profound. This object had to be unimaginably bright to be visible from so far. This set off a chain of calculations, measurements, and theories that eventually led to its classification as one of the most luminous quasars ever found, powered by what we now estimate to be the most massive known black hole in the observable universe. Its light, what little of it reaches us through intergalactic absorption and redshifting, is still bright enough to be studied in multiple wavelengths. From X-rays to ultraviolet to optical to radio, TUN 618 is a laboratory of astrophysical extremes. Its accretion disk, composed of gas and dust spiraling inward at relativistic speeds, is heated to millions of degrees, radiating fiercely as magnetic fields twist and snap and plasma jets shoot out at nearly the speed of light. These jets, extending possibly thousands of light-years, interact with the intergalactic medium, seeding it with high-energy particles and affecting the formation of nearby galaxies. This feedback mechanism, where a supermassive black hole regulates star formation in its host galaxy through radiation and jet activity, is a key component of modern cosmological models. And TUN 618, with its extreme output, helps validate and refine these models at their most intense boundaries. Its host galaxy, though not clearly resolved, is likely to be a giant elliptical or perhaps a massive proto-galaxy still forming in the early universe. The merger history of such a galaxy must be extreme, involving multiple collisions and inflows of gas. The conditions required to feed a black hole at this rate over such a long time suggest a rich and violent cosmic environment. TUN 618 is not just the product of its galaxy, it has helped shape it, mold it, and possibly prevent it from forming too many stars too quickly by heating and expelling gas. Moreover, the radiation pressure and relativistic outflows from its accretion disk would be so strong that they create a boundary condition known as the Eddington limit, a point beyond which the outward pressure of light balances the inward pull of gravity. And yet, TUN 618 seems to have either skirted or surpassed this limit at various times, hinting at mechanisms of super-Eddington accretion, perhaps through geometrically thick accretion disks or anisotropic radiation flows. This invites another fascinating possibility, that TUN 618 is a hyper-Eddington accretor, temporarily defying classical limits and forcing us to update our models of how black holes grow. Some theorists suggest that in certain dense, turbulent environments, black holes can feast on surrounding matter at rates previously thought impossible, hidden behind dense clouds of gas that absorb and re-emit the radiation more efficiently. If TUN 618 went through such a phase, it would explain how it became so massive in so little cosmic time. But the questions don't stop there. Could TUN 618 harbor a binary black hole system at its center, an even more massive black hole pair dancing around each other at sublight speeds? If so, gravitational wave detectors of the future, such as LISA, Laser Interferometer Space Antenna, could one day hear the subtle murmurs of their orbital decay. The implications of such a discovery would be staggering, providing a direct window into the most extreme gravitational interactions in the universe. And then there is the possibility that TUN 618 is not an isolated monster but part of a hidden population. Perhaps our current telescopes have simply missed others like it, obscured by dust, hidden at redshifts too high for current surveys, or camouflaged among less luminous quasars. Future telescopes like the James Webb Space Telescope, already operational, and next-generation radio arrays may uncover this secret zoo of ultra-massive black holes. If so, TUN 618 will be the first of many, not an anomaly but a herald of a new class of cosmic giants. Even more speculative are ideas rooted in alternative physics. Could such massive black holes be connected to dark matter? Might they form through the collapse of primordial density fluctuations seeded by quantum processes in the early universe? Could they even harbor exotic phenomena like white holes, wormholes, or connections to other universes? These ideas, while on the edge of current science, are not beyond consideration. Black holes have always challenged the boundaries of physics, from Hawking radiation to the information paradox to firewall theories and holographic principles. TUN 618, by virtue of its size, brings these issues into sharp focus. It is a natural laboratory for testing the limits of general relativity, quantum mechanics, thermodynamics, and information theory. Its sheer gravitational influence also invites reflection on time itself. Near the event horizon of TUN 618, time would slow to a crawl relative to an outside observer. The closer you get, the slower your clock ticks. From a certain perspective, events at the edge of the black hole happen in eternal suspension, never quite falling in, never fully escaping. The information paradox, that puzzle of how black holes can evaporate via Hawking radiation while seemingly erasing all the information that falls into them, gains new weight when scaled to something the size of TUN 618. This paradox, still unsolved, cuts to the heart of theoretical physics. Is information truly destroyed inside black holes, violating quantum mechanics? Or does it somehow survive, perhaps encoded on the event horizon as holographic data, as proposed by the holographic principle? Or is it released back into the universe in some subtle way during black hole evaporation? In the case of TUN 618, evaporation is a distant concern. It would take far longer than the age of the universe for such a black hole to shrink even slightly via Hawking radiation, but the principle remains. The larger the black hole, the deeper the mystery. And yet, despite all the complexity and strangeness, TON 618 is real. It is not a hypothetical object or a theoretical construct. It's an entity whose light reaches our detectors, whose gravitational signature can be inferred, whose mass can be estimated with confidence. It anchors our understanding of what black holes can become and challenges us to look deeper, further, and more fearlessly into the night sky. The existence of TON 618 forces us to reconsider the upper limits of mass and structure in the universe. Traditionally, scientists believe there must be a cap, a theoretical ceiling to how massive a black hole could grow within the age of the universe. But TON 618 breaks that ceiling wide open. If it could reach over 66 billion solar masses in less than 4 billion years after the Big Bang, what does that say about the mechanisms of accretion, galactic mergers, and the rate at which the cosmos builds structure? It may suggest that some black holes were born differently than we assumed. While many black holes are thought to begin as the remnants of massive stars, slowly growing through the ingestion of gas, dust, and stars, there may be another class altogether, the so-called direct collapse black holes. These theoretical objects form not from stars, but from massive clouds of primordial gas that collapse under their own gravity directly into black holes, skipping the star formation stage entirely. If TON 618 began as one of these, its head start on growth would explain much about its enormous size today. Even then, feeding such a beast would require an almost continuous inflow of mass, unimpeded by radiation pressure or galactic feedback effects. That means the surrounding environment of early TON 618 must have been exceptionally rich, cosmic filaments funneling cold gas directly into its center, galactic mergers delivering fresh material, and perhaps chaotic feedback loops regulating its diet. It turns the region around TON 618 into something akin to a galactic rainforest, dense, fertile, and filled with energy exchange. The presence of such a black hole also has implications for the evolution of the early universe. It lends credence to the theory that black holes helped regulate the pace of galaxy formation. In the chaotic youth of the cosmos, galaxies were still forming their structures. Without regulation, they might have produced stars too quickly, using up their gas and becoming quiescent prematurely. But with supermassive black holes like TON 618 at their centers, these galaxies had a thermostat, a powerful, luminous core capable of heating and expelling gas to slow down star formation. TON 618 didn't just sit at the center of its galaxy, it actively shaped its environment, sculpting matter and energy on galactic scales. That leads to a natural question: how far does its influence reach? In theoretical models, the sphere of influence of a supermassive black hole extends many light-years beyond its event horizon. This is the region where its gravity dominates over the collective pull of surrounding stars. For TON 618, this could mean a sphere stretching dozens, maybe even hundreds of light-years, a gravitational dominion so vast it could hold entire star clusters in sway. And as light from this monstrous quasar travels across the universe toward us, it passes through countless intergalactic clouds, absorbing certain wavelengths, and leaving a trail of cosmic breadcrumbs. By analyzing the absorption lines in its spectrum, astronomers can learn about the composition, motion, and density of the intervening medium, effectively turning TON 618 into a backlight for intergalactic exploration. Its radiation serves as a probe, not just into the object itself, but into the vast cosmic ocean that lies between us and it. The redshift of TON 618, measured at approximately 2.219, indicates that we see it as it was around 10.4 billion years ago. In other words, we're peering more than 2/3 of the way back to the beginning of the universe. It's a time machine as much as it is a celestial object. The photons we detect now began their journey when Earth was not yet formed, when the Milky Way was still assembling its stars, when the first galaxies were just beginning to shine. The existence of such a powerful quasar in this epoch helps refine our models of cosmic evolution. It means that, despite the darkness and chaos of the early universe, there were already mature, massive structures forming. And that's where things get truly philosophical. Because TON 618 isn't just a physical entity. It's a message from the past. A message about what is possible. A message about what kind of structures the universe can build. It tells us that the cosmos isn't limited by our imagination. That even the most extreme theoretical possibilities might have real, observable counterparts. It's a cosmic monument to the boundlessness of creation. Even now, researchers continue to analyze it, using not just optical and radio telescopes, but also data from infrared observatories and theoretical models. They simulate its formation, its light curves, its environment, and its potential companions. They wonder if perhaps other, even more massive black holes exist, hidden behind clouds of gas, lurking in deep fields, or shining faintly at the edge of detectability. In this search, TON 618 remains the benchmark, the gold standard for cosmic monstrosity. Its name, TON 618, might sound impersonal, like a serial number. But perhaps that's fitting. It reminds us that even the most profound objects in the universe can begin as cold data, discovered in catalogs, and only later revealed to be breathtaking cosmic wonders. Behind the sterile label lies a gravitational god, one whose presence bends not only space and time but also our very understanding of reality. Because TON 618 is more than just a black hole. It is a symbol of the universe's ability to astonish. It is a challenge to the limits of physics. It is a doorway to questions we have not yet learned to ask. And so we keep looking. Deeper. Farther. More precisely. Because somewhere out there, among the millions of galaxies, quasars, and unknown entities, there may be others like TON 618. Or perhaps even greater ones. And when we find them, they will tell us more about our origins, our future, and the fabric of the cosmos itself. Its sheer presence forces scientists to reevaluate not only how quickly black holes can grow but how large structures emerge from the primordial soup of the early universe. We know that the standard models of black hole growth, primarily through accretion disks and galactic mergers, work well for many supermassive black holes, but TON 618 pushes those models to their extreme. It begs the question, what unknown mechanisms might have contributed to its growth? Was its accretion somehow more efficient than anything we've ever observed? Was its environment uniquely conducive to unimpeded feeding? Or are we simply missing pieces of the cosmic puzzle? TON 618 might be the result of a cosmic perfect storm, an abnormally massive seed black hole born from the direct collapse of a gas cloud, situated in a rich galactic environment with few opposing forces, and allowed to grow uninterrupted for hundreds of millions of years. This possibility has stirred new interest in the study of early black hole formation, leading to refinements in our simulations and deeper scrutiny of high redshift objects. The study of quasars like TON 618 also brings attention to an even more enigmatic phase of cosmic evolution, the epoch of reionization. This is the period when the first stars and galaxies began reionizing the neutral hydrogen that filled the universe after the Big Bang. The intense radiation from early quasars, like TON 618, might have played a significant role in that transformation, acting as cosmic lighthouses that tore apart atoms and restructured the very nature of intergalactic space. By examining TON 618's emissions, astronomers are able to trace these transformations. For example, its ultraviolet output and X-ray signatures give clues about the high-energy processes near its event horizon. These signatures are not just academic curiosities. They allow astrophysicists to reconstruct the temperature, density, and magnetic environment of its accretion disk, a swirling maelstrom of gas, dust, and energy. Then there's the relativistic jet, a beam of particles traveling near the speed of light, launched from the poles of the black hole. Though not yet definitively confirmed in TON 618 due to observational limitations, it's highly likely that such a jet exists, given the intense energy output. These jets have far-reaching implications. They can heat interstellar gas, halt star formation in the host galaxy, and even distribute heavy elements across thousands of light years. If TON 618 is emitting one, it could have influenced not just its own galaxy but the surrounding cosmic web. The host galaxy of TON 618 is itself a mystery. We can infer its presence from the gravitational effects and the absorption lines in the quasar's spectrum, but we can't clearly observe it due to the quasar's overpowering brightness. However, if we assume it's a massive elliptical galaxy, like those hosting other supermassive black holes, then it's likely one of the most massive galaxies in the observable universe. Its stars, gas clouds, and dark matter halo would represent a colossal reservoir of mass and energy, all orbiting a black hole that dwarfs everything around it. Furthermore, TON 618 presents an intriguing challenge to our understanding of entropy and the second law of thermodynamics on a cosmic scale. Black holes are often described as the highest entropy objects in the universe. The more massive they are, the more entropy they possess. If TON 618 represents one of the most massive black holes known, then it may also be one of the most entropic structures in the cosmos. That makes it not just a gravitational anomaly, but a thermodynamic marvel. There's also a fascinating philosophical dimension to TON 618. When we observe it, we are looking at an event that occurred billions of years ago, and yet, we only experience it now. It is an echo of the past, a fossil of light stretched across time. And in a sense, TON 618 exists in a realm that no longer resembles what we see. Its light is a relic. The black hole itself may have changed drastically, merged with others, or even grown larger. It may now be part of a different galactic structure, or it may have quieted, no longer a quasar, now cloaked in darkness. Still, the light it emitted then continues to reach us, telling its story across the void. TON 618 becomes a testament to the nonlinear nature of cosmic observation. We are not seeing the universe as it is, we are seeing it as it was. And that temporal disconnect is central to our pursuit of knowledge. Every image from space is a look into the past. Every distant quasar is a messenger from an ancient era. In that sense, TON 618 is not just an object of study, it is a storyteller, a voice from a time before Earth even existed. It challenges the scale at which we think about the universe. With a mass of over 66 billion suns, it makes even our entire Milky Way galaxy, home to 200 billion stars, seem modest. It compels us to redefine what we mean by large, massive, and extreme. And this isn't just for curiosity's sake. The true scale of TON 618 could impact our calculations of the mass density of the universe, which in turn feeds into our models of cosmic expansion and the eventual fate of all existence. Even the numbers associated with it are difficult to grasp. The Schwarzschild radius of TON 618, a measure of the size of its event horizon, would be more than 1,300 astronomical units, or about 0.02 light-years. That's more than 30 times the distance from the Sun to Pluto. Imagine an invisible sphere of no return that vast. Anything that crosses that boundary is lost forever, pulled into a region where even time and space lose their meaning. It is a sphere of silence in the cosmic symphony, a place where known physics collapses into singularity. And yet, despite its enormity and gravity, we can study it. We can measure its light, estimate its mass, infer its environment, and even simulate its evolution. That is the true triumph of human ingenuity, to be able to extract understanding from the darkness. In this pursuit, we use every tool at our disposal: spectroscopy, photometry, redshift calculations, computer simulations, and more. TON 618's redshift of 2.219 tells us that the light we see now was emitted over 10 billion years ago. That's nearly 75% of the way back to the beginning of the universe. To understand the significance of this number, consider what it means for light to travel that distance. Each photon from TON 618 began its journey when Earth didn't even exist, when our solar system was nothing more than cold dust floating in interstellar space. Those photons have crossed cosmic voids, dodged galaxies, skirted stars, and finally, after a journey of eons, ended their flight in the detectors of our telescopes. The spectral lines that we observe, broad, luminous, and redshifted, are more than just graphs. They are the voice of TON 618, distorted by its immense velocity and warped by the gravitational fields that surround it. These lines let us determine the composition of the accretion disk, the velocity of the orbiting material, and even the orientation of the quasar relative to Earth. It's a cosmic fingerprint, a signature of something that exists beyond the edge of comprehension. Delving deeper into the structure of this behemoth, let's consider the mechanics of its accretion disk. At such an extreme mass, the disk isn't just a flat whirlpool of material. It's a thermonuclear storm, glowing white-hot and emitting energy equivalent to trillions of stars. The inner parts of the disk spiral in at relativistic speeds, heating up to millions of degrees Kelvin. This is where the intense ultraviolet and X-ray radiation originates. The outer regions, cooler but still violent, feed the inner core with a never-ending stream of matter, like a conveyor belt into oblivion. Surrounding this structure, we find the broadline region, a zone of fast-moving clouds of gas that emit the prominent emission lines we use to classify quasars. These clouds orbit at speeds of thousands of kilometers per second, ionized by the ultraviolet radiation from the disk. Further out is the narrow-line region, where gas moves more sedately and the radiation is less intense. Beyond that lies the host galaxy, whose shape and scale remain hidden behind the brilliance of the quasar. Yet, even further out lies the influence of TON 618's dark matter halo. Like every massive galaxy, TON 618's home is embedded in a halo of invisible mass, dark matter that we cannot detect directly but know must be there from the way light bends and gas moves. This halo may extend hundreds of thousands of light-years, cradling the galaxy and influencing nearby structures. It's a silent partner in the saga of the black hole's growth, shaping its environment, while remaining undetectable to our eyes. Another extraordinary consideration is the Eddington limit, the maximum luminosity a black hole can achieve before the outward pressure of radiation counteracts the inward pull of gravity. For a black hole of TON 618's size, that limit is staggeringly high. Yet the fact that it shines so brightly suggests that it may have spent considerable time accreting matter near, or even beyond, this theoretical threshold. If true, it could indicate that our understanding of accretion physics is incomplete. Some theories propose super Eddington accretion phases, where the structure of the disk changes, allowing more material to fall in without blowing itself apart. Others suggest that black holes like TON 618 had prolonged periods of uninterrupted feeding, shielded by dense inflows of gas that funneled mass directly into the center. Moreover, TON 618 may be a relic of an earlier phase in black hole formation theory, what astrophysicists sometimes call direct collapse black holes. These theoretical giants could form without the need for a supernova or the death of a star. Instead, under special conditions, an enormous cloud of primordial gas might collapse directly into a black hole of thousands, or even millions of solar masses. If TON 618 began as such a seed, then it had a head start in the cosmic race to become supermassive. This could explain how it became so enormous so early in the universe's history, and why so few similar black holes have been found. They're simply too rare or obscured by the fog of time. Its rarity itself is part of its allure. TON 618 is unique among known quasars not just for its mass but for its luminosity and distance. While we've identified many quasars at similar redshifts, few possess the sheer power of TON 618. This has led some to speculate that we may have only seen the tip of the iceberg. There could be others, hidden behind dust, veiled by intergalactic gas, or too far away for even our most powerful telescopes to detect. To find them, scientists are planning and executing ever more sensitive surveys. Instruments like the James Webb Space Telescope, with its infrared capabilities, may one day pierce the fog and reveal more titanic black holes lurking in the early universe. Likewise, next-generation observatories like the Vera C. Rubin Observatory and the extremely large telescope will provide even more powerful means to identify quasars from the universe's infancy. Each discovery will help refine our models, map our cosmos more clearly, and perhaps bring us closer to understanding how something like TON 618 came to be. TON 618 also sparks speculative discussions beyond conventional science. Could such immense gravitational wells serve as natural laboratories for testing general relativity under extreme conditions? Could their environments reveal clues about quantum gravity, the yet untamed union of Einstein's relativity and quantum mechanics? Some theorists propose that near the event horizon of a black hole like TON 618, strange effects, gravitational time dilation, frame dragging, or quantum information paradoxes, could manifest in ways that might one day be observable. And while these remain theoretical, they continue to inspire physicists and cosmologists to push the boundaries of understanding. Ton 618 may hold answers to questions we don't even know how to ask yet. Ton 618 also raises the stakes in a much broader cosmic mystery: the role of supermassive black holes in galaxy formation and evolution. Traditionally, galaxies and black holes were thought of as separate entities, the galaxy a vast sea of stars and gas, and the black hole a compact anomaly at the center. But observations over the last few decades have completely rewritten that narrative. We now know that the mass of a supermassive black hole correlates strongly with the properties of its host galaxy, particularly the mass of the galactic bulge and the velocity dispersion of its stars. This is known as the M-sigma relation, and it suggests a deep, almost symbiotic relationship between black holes and galaxies. Ton 618, given its massive scale, forces us to ask, what kind of galaxy could host such a black hole? If the black hole weighs 66 billion times the mass of the Sun, then the galaxy itself may be a titan among titans, perhaps a central galaxy in a massive cluster, enriched by mergers, fed by streams of cold gas, and stabilized by an enormous halo of dark matter. But since the black hole outshines its host, we struggle to see the galaxy directly. This introduces one of the great observational challenges. How can we peel away the glare of the quasar to glimpse the home it resides in? Astronomers have developed clever techniques for this. One involves using gravitational lensing, where a foreground galaxy bends and magnifies the light of a background quasar, to enhance our view. Another relies on modeling the quasar's light and subtracting it from the image, leaving behind a faint trace of the galaxy beneath. These approaches, while technically demanding, have already borne fruit in other systems. Applying them to TON 618 could one day reveal the full extent of the colossus that surrounds this cosmic beast. And then there's the matter of its jets. TON 618, like many quasars, may possess relativistic jets that shoot out from its poles at near light speeds. These jets are powered by the black hole's spin and the twisted magnetic fields in its accretion disk. They're not just side effects, they're capable of influencing entire galaxies, injecting energy into the interstellar medium, regulating star formation, and carving out enormous radio lobes that stretch for hundreds of thousands of light years. If TON 618 has jets, they might be among the longest and most powerful in the universe. Detecting them and mapping their structure could reveal new dimensions to this already mesmerizing object. Jets also speak to the black hole's rotation. A spinning black hole drags space-time itself around with it in a phenomenon called frame dragging, or the lens-stirring effect. This isn't just a theoretical curiosity, it has practical implications. The spin determines how efficiently the black hole can convert infalling matter into energy. A rapidly spinning black hole can shine brighter and power stronger jets. If TON 618 is a fast rotator, that might help explain its incredible luminosity and its capacity to feed at such an accelerated pace in the early universe. But how did it acquire such a spin? One possibility is through a series of mergers with other black holes. In the chaotic early universe, galaxies frequently collided and merged, and their central black holes often coalesced as well. Each merger would not only increase the mass of the resultant black hole but could also impart spin, depending on the angular momentum of the two black holes involved. Over time, this process could create a rapidly spinning, massively heavy black hole like TON 618. The gravitational waves produced by such mergers are another frontier of study. TON 618 may be a relic of such cataclysmic events, and while we can't detect gravitational waves from that far back yet, future observatories, such as the space-based LISA, Laser Interferometer Space Antenna, might one day catch echoes of similar events. This would not only confirm aspects of TON 618's formation but open a new window into the early universe. Meanwhile, the very idea of such mass and density bends our understanding of physical limits. According to general relativity, once matter crosses the event horizon, it collapses toward a singularity, a point of infinite density where our known laws of physics break down. But quantum theory refuses to accept this singularity as a complete description. Some suggest the core of a black hole might be a Planck star, or quantum gravity effects prevent total collapse. Others imagine black hole cores, composed of exotic matter, or even wormhole connections to other universes. While these ideas remain speculative, TON 618 acts as a test case for the extremes of theory. Any model of black holes must ultimately account for the behavior of something this large, this old, and this active. It is the ultimate stress test for our theories of gravity, quantum mechanics, thermodynamics, and cosmology. As such, it doesn't just sit at the center of its galaxy, it looms at the crossroads of modern physics. And in the context of the universe's lifespan, TON 618 provides a sobering anchor. It reminds us that the cosmos is a place of unimaginable extremes. On one hand, we have the delicate birth of stars and planets, the dance of galaxies, and the gentle background hum of the cosmic microwave radiation. On the other, we have this Leviathan, a devourer of light, a warper of space, a monument to collapse and consumption. And yet, both ends of that spectrum coexist, each shaping the universe in their own way. Perhaps the most haunting aspect of TON 618 is what it implies about the future. Black holes are eternal, or nearly so. They evaporate through Hawking radiation, but for a black hole this large, the evaporation time exceeds the age of the universe by trillions upon trillions of years. Long after the last star has faded, long after galaxies have disintegrated, long after even protons may have decayed, TON 618, or what remains of it, will persist. A lonely shadow in a dead universe, radiating nothing, consuming nothing, merely existing. This, too, is part of its mystique. TON 618 is a reminder that the universe is not made for comfort. It is vast and indifferent, and it contains forces beyond our comprehension. But within that indifference lies beauty. A beauty that we, as a tiny species on a pale blue dot, have glimpsed and understood in part. And that act of understanding, that curiosity to peer across the eons and decipher the whisper of ancient photons, is what sets us apart. It is what connects us to TON 618, not just as observers, but as participants in the grand narrative of the cosmos. In continuing the epic journey through the depths of TON 618, we find ourselves entering territory that transcends conventional cosmic structures. To fully grasp the grandeur of this behemoth, we must understand not only the direct mechanics of black holes and quasars but also the deeper layers of astrophysical phenomena that help sustain and shape them. TON 618, due to its sheer scale, becomes a proxy for every cosmic process pushed to its absolute extreme: energy generation, mass accumulation, and the influence of gravitational mechanics on universal structure. Let us delve more deeply into the concept of accretion, a process that is at the very heart of TON 618's staggering luminosity. Accretion is more than just matter falling into a gravitational well. It is one of the most efficient energy-generating processes known to modern physics. When gas and dust spiral inward toward a black hole, they form a structure known as an accretion disk. This disk is not merely a passive funnel but a dynamic, thermodynamically volatile region that heats up to millions of degrees due to friction and gravitational compression. In the case of TON 618, the accretion disk is so intense that it outshines the entire galaxy that hosts it, producing more light than trillions of stars combined. The mechanisms here are so efficient that up to 10% of the mass energy of the infalling matter is converted into radiation. By comparison, nuclear fusion in stars like our Sun only converts about 0.7% of mass into energy. This incredible efficiency is what makes quasars, and TON 618 especially, such luminous beacons visible across the universe. Yet, this energy does not emanate equally in all directions. TON 618's quasar properties may include anisotropic emissions, meaning its radiation is emitted preferentially in certain directions. This could potentially alter how we perceive its luminosity and true energy output depending on our line of sight. Advanced simulations and models suggest that quasars, especially those fueled by supermassive black holes like TON 618, often exhibit funnel-like regions of intensified emission perpendicular to their accretion disks. Further adding to this complexity is the concept of the broadline region (BLR). This is an area surrounding the black hole where clouds of ionized gas, moving at incredibly high velocities, produce broadened spectral emission lines due to the Doppler effect. By studying these lines, astronomers can estimate the velocity of the gas, and through that, infer the mass of the black hole. For TON 618, such analyses have revealed line widths so broad they suggest gas moving at tens of thousands of kilometers per second, yet another indicator of the mind-bending gravity at play. Moving outward, the narrowline region, NLR, exists further away from the black hole, where gas clouds are slower and cooler. Even these outer regions in TON 618's environment exhibit dramatic activity, including high ionization levels and energy transfer across light years of space. This again hints at the titanic scale of the system. Its influence spreads well beyond the event horizon, or even the accretion disk, shaping the galactic and intergalactic medium. One must also consider the torus, the thick, donut-shaped cloud of gas and dust that encircles the black hole and its accretion disk. This torus can obscure certain wavelengths of light, especially in the optical range, and can explain variations in brightness and spectral properties among quasars. The exact composition and orientation of TON 618's torus remain subjects of speculation, but it's likely composed of materials heated to such high temperatures that they radiate in the infrared, contributing further to its signature across the electromagnetic spectrum. Speaking of the spectrum, TON 618 emits not just visible light but across nearly the entire electromagnetic spectrum, from radio waves to X-rays and possibly even gamma rays. Each band tells a different part of the story. For example, radio emissions might map out the presence of relativistic jets, while X-rays provide insight into the innermost parts of the accretion disk where matter is nearest to the event horizon. High-resolution spectroscopy in these bands is helping us build a more comprehensive picture of what life near TON 618 looks like. Let's also reflect upon the implications of Eddington luminosity, a theoretical limit on the brightness of an object where the outward pressure of radiation balances the inward pull of gravity. When an object reaches this limit, any additional infalling matter is pushed away by the force of its own light. TON 618 is likely operating at or near this limit, which suggests a state of dynamic equilibrium between accumulation and expulsion of matter. Some theories even propose it may temporarily exceed this limit in episodes of super-Eddington accretion, likely due to instabilities or complex geometries in the accretion disk. Such phenomena open the door to questions of black hole growth. How could a black hole grow so massive without constantly blowing away its own fuel? This conundrum challenges traditional growth models. While steady accretion over time is a reliable path for small and medium black holes, it is likely insufficient for creating a monster like TON 618 within the age constraints of the early universe. This brings us again to the concept of direct collapse, where instead of a star dying and collapsing into a black hole, a vast cloud of primordial gas may have skipped star formation altogether and directly formed a black hole thousands of times the Sun's mass. These seed black holes, especially if formed in dense regions of early cosmic structure, could grow rapidly through episodes of chaotic accretion and merger events. Some models even speculate that in the early epochs of the universe, conditions were uniquely favorable for such explosive black hole growth. The higher density of matter, elevated rates of galaxy interaction, and abundant cold gas streams feeding the central regions may have created a perfect storm for supermassive black hole formation. TON 618 may represent one such outcome, a rare but vital clue into how quickly and dramatically the cosmic environment could evolve in those first few billion years. It reminds us that the universe did not start as a quiet, slowly aging entity. It was instead a violent, dynamic crucible where extreme objects like TON 618 emerged from the cosmic chaos. And then, there is gravitational lensing, a natural cosmic magnifier that occurs when the light from a distant object like TON 618 is bent and focused by a massive object, such as a galaxy cluster, lying between it and Earth. If TON 618 were aligned just right with a foreground cluster, gravitational lensing could dramatically enhance its visibility, making it appear brighter and more distorted in our telescopes. Some have speculated whether lensing may play a role in how we perceive TON 618's luminosity, although there's no strong evidence yet to support this. Still, it's a valuable consideration in the broader context of observational cosmology. As we contemplate these complexities, we must also consider the long-term fate of TON 618. Over cosmic time, black holes don't simply remain static. Their feeding rates change. Their environments evolve. Galaxies merge, gas gets consumed or ejected, and black holes eventually enter a quiescent state. It's possible that TON 618 may already be past its most active phase. What we observe today could be the light from a period long gone, perhaps billions of years ago when it was in its prime. That's the nature of astronomical observation. We see everything in retrospect, gazing into ancient light that took eons to reach us. The idea that TON 618 may already be dormant introduces philosophical implications. We are witnessing the echo of an entity that may no longer even shine, yet its ancient radiation continues to tell its story across the vast corridors of spacetime. This fact underscores the time-warped nature of cosmic observation, an act of seeing the past, reconstructing events from long before the Earth was even born. As we reflect on this, we begin to see that TON 618 is more than just an astrophysical object. It's a monument to extremes. It stands as a pillar in our understanding of black holes, quasars, galaxy formation, and the early universe. Its very existence challenges assumptions, stretches the bounds of theoretical models, and inspires new lines of inquiry. The very notion that we, fragile beings clinging to a small rock in the outskirts of a spiral galaxy, can detect, study, and begin to understand such a leviathan, is a testament to the power of human curiosity and ingenuity. Through vast telescopes, sophisticated algorithms, and theoretical models, we reach across billions of light years and billions of years of time to hold TON 618 in our scientific grasp, even if for just a moment. And yet, this journey is far from over. As we press deeper into the mysteries surrounding TON 618, one essential question lingers in the minds of astronomers and cosmologists alike. What lies beyond the observable phenomena? While we've discussed its mass, radiation, and the processes feeding its growth, TON 618 also forces us to confront the deepest enigmas of space-time, quantum mechanics, and the very architecture of the universe. Black holes, especially ones as massive as TON 618, are thought to influence not only their immediate environment, but also the fabric of spacetime itself. According to Einstein's theory of general relativity, any object with mass warps the spacetime around it. But when that object is a black hole weighing more than 60 billion solar masses, the curvature becomes so extreme that space and time behave in unfamiliar, almost surreal ways. The region near the event horizon of TON 618 is a domain where time dilates severely, where seconds for infalling matter stretch to millennia from an outside observer's perspective. This distortion has profound implications. If we could somehow hover just outside the event horizon of TON 618, protected by some impossible technology, time would seem to nearly stop relative to the universe beyond. Stars would accelerate across the sky. The entire cosmos might evolve in a blur. In this sense, TON 618 is not merely an object, it's a gateway to relativistic extremes, where even our most basic intuitions about time and space break down. But the story becomes even stranger when we look at TON 618 through the lens of quantum mechanics. According to the laws of quantum theory, information cannot be destroyed. This creates a paradox when dealing with black holes, which seem to obliterate all details of the matter that falls into them. This is known as the black hole information paradox, and TON 618, due to its sheer scale, becomes a colossal laboratory for this cosmic riddle. Does information falling into TON 618 truly vanish forever? Or is it somehow preserved, perhaps encoded in the Hawking radiation that, at least theoretically, is emitted from the event horizon over astronomical timescales? Hawking radiation itself has never been directly observed, especially not from something as massive as TON 618, since its temperature would be just above absolute zero. But in theory, over unimaginable epochs, TON 618 would slowly radiate away its mass, eventually evaporating completely, if left undisturbed for many trillions of years. However, the timescale of this process is so immense that, for all practical purposes, TON 618 is eternal. It would outlast all stars, all galaxies, and perhaps even the very concept of structure in the universe. It could become one of the last remaining witnesses to the universe's final fate, a solitary behemoth drifting through a cold, dark cosmos long after everything else has faded into entropy. And what of the region inside? Though we cannot observe past the event horizon, theories abound about what exists at the center. Classical physics suggests a singularity, a point of infinite density where the laws of physics break down. But modern theories, such as loop quantum gravity or string theory, propose alternatives, perhaps a region of incredibly dense but finite matter, or even a gateway to another universe or dimension. Could TON 618 be a cosmic bridge to elsewhere? A wormhole in disguise, a throat through which matter could pass into another realm? While speculative, these ideas are not dismissed lightly. The nature of such massive black holes may hold the key to a future unification of gravity and quantum mechanics, the elusive theory of everything. By understanding the structure, behavior, and origin of giants like TON 618, we inch closer to solving some of the most profound mysteries of existence. Meanwhile, there's the broader cosmic role of such black holes. TON 618 may not merely be a passive consumer of matter but an active shaper of galactic architecture. Observations of other galaxies reveal that the mass of their central black holes correlates closely with the properties of the galactic bulge, suggesting a feedback mechanism. It's possible that TON 618 once helped regulate star formation in its host galaxy through intense radiation and energetic outflows, pushing gas away and stifling the birth of new stars. This relationship between supermassive black holes and their host galaxies is one of the most intriguing in modern astrophysics. It suggests a coevolutionary process where galaxies and black holes grow in tandem, each influencing the other. In the case of TON 618, this interplay would have occurred on a truly grand scale, potentially shaping not only its galaxy but the larger structure of the cosmic web around it. And that brings us to a final, awe-inspiring thought. TON 618 may not be unique. It may be the most massive black hole we've measured with confidence, but it may not be the most massive that exists. There could be others, silent, invisible, hiding in regions of space we cannot yet observe, perhaps obscured by dust, dormant without an active accretion disk, or simply too far away for their light to have reached us. The cosmic darkness may be littered with other giants, each with their own history, their own galaxies, and their own influence on the universe. In that sense, TON 618 is both a marvel and a harbinger. A reminder that the universe is filled with extremes we are only beginning to comprehend. A beacon from a time long past, yet still bright enough to pierce the cosmos and reach us here on Earth. A structure so vast it challenges the limits of imagination, yet so real it forces science to evolve just to understand it. The story of TON 618 is the story of cosmic ambition, of gravity pushed to its furthest limit, of matter shaped into light, and of a universe that dares to build something that defies every earthly scale. It stands not only as the heaviest object we've found, but perhaps as one of the most beautiful expressions of cosmic law, a perfect paradox, a void that shines brighter than anything else. And still, there is more to uncover. As we peer even deeper into the enigma that is TON 618, we find that this colossus does more than just challenge our understanding of black holes. It acts as a crucible for new theories, as a canvas for cosmic questions, and as a silent witness to the evolution of the early universe itself. Its presence is not simply a curiosity or an oddity on the far edges of an astronomical catalogue. It is a puzzle piece, perhaps one of the most essential, in the cosmic narrative that stretches across time and space. What truly sets TON 618 apart is not only its mass, which is gargantuan beyond ordinary human conception, but its age and brightness. Located an estimated 10.4 billion light-years from Earth, TON 618 formed when the universe was only about 3.4 billion years old. This means that in just a small fraction of the universe's lifespan, it had already accumulated over 60 billion solar masses. The implications of this are staggering. How did such a massive black hole form so quickly after the Big Bang? This question reverberates through the halls of modern astrophysics and cosmology. Conventional black hole growth models, which rely on the accretion of gas and the merging of smaller black holes, struggle to account for the sheer size of TON 618 in such a short cosmic time span. If TON 618 followed the usual growth curve, it would have needed far more time than the universe had existed up to that point to achieve its size. This discrepancy forces scientists to consider alternative formation scenarios. One possibility is the concept of direct collapse black holes. In this model, instead of forming from the remnants of massive stars, certain regions in the early universe may have collapsed directly into black holes without fragmenting into stars first. These seed black holes could be thousands or even millions of solar masses from the outset, giving them a significant head start. Under the right conditions, extremely dense gas, minimal radiation feedback, and isolation from disruptive forces, these direct collapse black holes could rapidly grow into supermassive black holes like TON 618. Another possibility is super-Eddington accretion, where a black hole consumes matter at rates exceeding the theoretical maximum luminosity allowed by the Eddington limit. Normally, the radiation pressure from intense accretion would blow away incoming gas and regulate the growth of a black hole. But in some extreme environments, such as those rich in dense, cold gas, this limit might be breached, allowing for runaway growth. If TON 618 underwent prolonged episodes of such super-Eddington feeding, its current mass becomes slightly more understandable. Yet another hypothesis considers primordial black holes, hypothetical black holes that could have formed in the first moments after the Big Bang due to quantum fluctuations and extreme density variations in the young universe. Though no direct evidence has confirmed their existence, if even a few such objects were created with masses large enough, they might have served as seeds for rapid growth into the giants we observe today. In this light, TON 618 could be a relic from a primordial era, a vestige of the universe's chaotic and fiery birth. But all of these are theories, highly educated, meticulously modeled, and compelling theories, yet unconfirmed. TON 618 remains as much a mystery as a clue. Every observation we make of it, every calculation and simulation, yields more questions alongside partial answers. In many ways, that is the nature of science, peeling back one layer of mystery only to find another beneath it. From a technological standpoint, studying something like TON 618 is a monumental achievement. The object is so distant that its light has been traveling toward us for more than 10 billion years. When we observe it through our most powerful telescopes, we are seeing it not as it is now, but as it was in a distant, ancient epoch. It's a message in a bottle, drifting across the cosmic sea for eons before finally arriving in our detectors. We study its emission lines, the spectra of its accretion disk, the Doppler shifts in its light. We analyze how its radiation interacts with surrounding gas. We compare its signature with models of black hole growth and galaxy formation. And we do all of this with instruments placed both on Earth and in space, massive arrays of glass and silicon that, together, function like cosmic eyes trained on the abyss. There is also the philosophical weight that TON 618 carries. What does it mean to discover something so immense, so ancient, and so distant? In some ways, it evokes a sense of cosmic humility. We often speak of our technological progress and our mastery over the natural world, but the existence of TON 618 reminds us of the scale on which the universe operates, a scale that dwarfs our entire planet, our history, and even our species. To put it into perspective, if the solar system were reduced to the size of a grain of sand, TON 618 would be a mountain the size of Earth itself. Its event horizon, the point of no return, spans hundreds of billions of kilometers, larger than the orbit of Neptune. And yet, despite all of that, it is still just a single black hole among billions, perhaps trillions, scattered across the cosmos. And this brings us to yet another intriguing possibility. TON 618 might not even be the largest. It is simply the largest we've been able to detect with current technology and observational limits. Future surveys, such as those using the James Webb Space Telescope, the Vera-C, Rubin Observatory, or next-generation X-ray telescopes, may reveal even more massive black holes lurking in the shadows. Perhaps there is a TON 620, or a TON 700, whose mass dwarfs even this cosmic titan. The very act of searching for these objects is a journey into the unknown. Every advancement in our observational tools widens the window into the distant universe, allowing us to detect fainter and more ancient light. With time, we may not only find black holes more massive than TON 618, but also uncover the processes that forged them, the galaxies they inhabit, and the role they played in the cosmic story. Yet, despite our growing knowledge, TON 618 retains its place as a symbol. It is a monument to scale, a celebration of extremes, a gravitational cathedral towering silently across billions of light years. It forces us to question what is possible, both in terms of physics and in our own quest for understanding. Even the name, TON 618, carries a kind of mythic simplicity. It was named as part of the Tonninsula catalog, essentially a designation in a database of celestial objects, yet it now stands as one of the most discussed and awe-inspiring entries in that archive. In the vast ledger of the universe, this one entry commands attention, not through color or proximity or visibility to the naked eye, but through sheer, staggering mass. And so, as we continue our journey, we do so with TON 618 as a kind of cosmic companion, not one we can ever visit, not one we can ever fully understand, but one whose existence enhances our own. It stands as a boundary marker for knowledge, a horizon in both the literal and metaphorical sense. To study it is to embrace the unknown, to peer into the ultimate expressions of gravity, time, and light. In the swirling depths of cosmic phenomena, TON 618 becomes more than just a supermassive black hole, it becomes a metaphor for the outer limits of comprehension. Scientists, philosophers, engineers, and poets alike might look upon its distant glow, an accretion disk of blinding brilliance encircling the ultimate darkness, and see a mirror of the unknown, a celestial echo of the questions we ask about existence itself. The accretion disk of TON 618 is not merely a luminous ring. It is one of the brightest continuous sources of energy ever observed from a single point in the universe. This brightness arises from matter that spirals inward at nearly the speed of light, heating up to millions of degrees, and releasing vast quantities of electromagnetic radiation before it disappears forever beyond the event horizon. It glows across the entire electromagnetic spectrum, from X-rays to ultraviolet to visible light, and that energy, after traveling for over 10 billion years, eventually reaches Earth, where it registers as a quasar. Quasars are among the brightest and most energetic objects in the universe, and TON 618 is one of the most extreme examples of this class. Quasars are thought to be powered by supermassive black holes at the centers of young galaxies, and they emit such intense radiation that they can outshine their host galaxies by factors of thousands. For TON 618, its quasar light is so intense that it was discovered because it looked like a star, but one emitting unusual ultraviolet spectral lines. It was these lines that first hinted at its true nature, not a star, but a remote, ravenous black hole surrounded by an accretion disk blazing like a cosmic furnace. This light, the very light we use to study TON 618, tells us about its composition, its velocity, and even its distance. By using redshift, how much the wavelength of light stretches as the universe expands, we can determine just how far away TON 618 is. And through careful modeling of its spectral emissions, we can estimate the mass of the black hole causing the energy emissions we see. That's how astronomers arrived at the now famous figure, 66 billion times the mass of our Sun. But the light also poses an intriguing paradox. How can such an intense beacon form so early in the universe's life? If TON 618 was already so massive when the universe was just a few billion years old, it implies a form of cosmic growth that we have yet to fully understand. The traditional models, including slow, steady feeding or even mergers between many smaller black holes, simply don't account for that level of mass so early. It's like meeting a fully grown redwood tree just a few years after planting a seedling. It challenges our assumptions and beckons us toward deeper understanding. This has led to a burst of activity in theoretical astrophysics. Researchers have proposed everything from modified accretion physics, to exotic particle interactions, to entirely new mechanisms for black hole growth. Some have even suggested that the rules of gravity may operate differently at the scale and density of early universe black holes. Could dark matter play a role? Could quantum effects accelerate black hole formation under certain conditions? These ideas are still speculative, but they demonstrate the power of TON 618 as a driver of scientific inquiry. And yet, for all its mystery, TON 618 is just one black hole among the estimated 100 billion galaxies, each with potentially millions of black holes. The fact that TON 618 stands out so starkly means it has something special about it, or that many more like it are waiting to be discovered. This leads to a new scientific frontier, the search for ultramassive black holes, sometimes abbreviated UMBHs. These are black holes with masses above 10 billion solar masses. TON 618, at over 60 billion, is far beyond that threshold. It also raises the question, what is the upper limit for a black hole's mass? Is there one at all? In theory, there's no clear limit to how massive a black hole can be. Given enough time and matter, any black hole could continue growing indefinitely. But in practice, various factors constrain this growth. Feedback from radiation, gravitational interactions with other objects, and limits on the amount of available infalling matter all conspire to keep black holes from growing unchecked. Yet TON 618 suggests that under the right circumstances, those limits can be pushed to extremes. It may represent a kind of peak performance in the black hole universe, a rare convergence of conditions allowing unprecedented mass accumulation. Let's pause for a moment and consider what that mass actually represents. 66 billion solar masses means that TON 618 weighs more than the combined mass of all the stars in a large galaxy. It's difficult to visualize such numbers, but we can try. Our Sun, which dwarfs all planets in the solar system, is just a tiny speck compared to this black hole. Multiply the Sun by 66 billion, and you still haven't fully grasped the scale of TON 618. If it were somehow placed at the center of the Milky Way, it would devour not just stars, but entire star systems, bending space around it like an unimaginable whirlpool of gravity. The event horizon of TON 618, the boundary beyond which nothing can escape, is estimated to be over 390 billion kilometers in diameter. That's about 2,600 astronomical units, or 2,600 times the distance from Earth to the Sun. That's so large it would easily swallow the entire solar system many times over. And yet, from the outside, it would appear deceptively simple, a black sphere, perfectly round, emitting no light, warping the stars behind it. And what lies beyond that event horizon? That question strikes at the heart of one of physics' most persistent mysteries. According to general relativity, once you cross the event horizon, you're inexorably drawn toward the singularity, a point of infinite density where the laws of physics as we know them break down. But quantum mechanics tells us that infinities are a sign that a theory is incomplete. Many physicists believe that a theory of quantum gravity, something that merges Einstein's relativity with quantum theory, is needed to describe what really happens at the heart of a black hole. There are competing models. Some propose that the singularity is replaced by a Planck core, a quantum object with immense density but finite size. Others suggest black holes may contain wormholes, tunnels through space-time that could, theoretically, lead to distant parts of the universe or even to other universes entirely. Some have gone further and suggested that what we think of as black holes might be fuzzballs, where the event horizon is replaced by a tangled mass of quantum strings. All of this remains speculative, of course. But the existence of extreme objects like TON 618 forces these questions to the forefront. It demands answers, not just from observers and experimentalists, but from theorists grappling with the fundamental nature of space, time, and matter. Another curious implication of TON 618 lies in its relationship with its host galaxy. Normally, black holes grow in tandem with their galaxies. There's a correlation called the M-sigma relation, which links the mass of a galaxy's central black hole with the velocity dispersion of the stars in the galaxy's bulge. This suggests some kind of coevolution, possibly regulated by feedback from the quasar phase, when black holes eject powerful jets and winds that can heat or expel gas, regulating star formation. But in the case of TON 618, its black hole mass seems to vastly exceed what we would expect from this relationship. Either its host galaxy is enormous and hard to detect due to the glare of the quasar, or this is a case of runaway black hole growth. Perhaps TON 618's host galaxy was cannibalized by mergers with other galaxies, providing ample fuel for growth. Or perhaps the rules that govern coevolution in the modern universe didn't apply the same way in the early cosmos. Whatever the case, TON 618 represents a kind of extreme outlier. It's a cosmic anomaly, an object so massive, so luminous, and so distant that it stretches every theory to the breaking point. TON 618 is not just an astronomical curiosity, it's a cosmic giant that forces us to re-examine fundamental ideas in astrophysics. It challenges everything we thought we knew about black hole formation, mass accumulation, and the evolution of galaxies. As we explore the implications of such an enormous object, we are drawn deeper into the heart of the universe, where some of its most profound mysteries lie hidden. While the sheer size and mass of TON 618 might seem to place it in a class of its own, it is important to understand that this supermassive black hole may not be as unique as it initially seems. There are other supermassive black holes that challenge our current understanding of the universe, and many of these are located in distant galaxies, some even older than our own. The discovery of TON 618 may well be the first step toward uncovering a population of similarly massive black holes, each potentially holding new secrets about the early universe. For example, a large portion of the universe is made up of quasars, luminous beacons of radiation powered by supermassive black holes. Though TON 618 is among the largest, it's possible that more giant black holes await discovery, hidden in the farthest reaches of the observable universe. These discoveries are still in their infancy, and with the advent of more powerful telescopes and advanced detection techniques, astronomers are beginning to push the boundaries of what we can observe. The James Webb Space Telescope, for example, has the potential to uncover previously unknown quasars, providing even more insight into the extreme conditions that give rise to objects like TON 618. The continued study of TON 618 also poses an opportunity to investigate the behavior of black holes in the context of the early universe. Observing such a massive black hole, which existed just a few billion years after the Big Bang, raises important questions about the formation of these cosmic titans. Could black holes of this magnitude have formed so early in the history of the universe, or did they grow over time? How did matter and energy come together to create such an intense gravitational pull? A popular theory is that supermassive black holes like TON 618 might have formed from the collapse of enormous gas clouds in the early universe. These gas clouds, made up of hydrogen and helium, could have condensed under their own gravity to create the first generation of black holes. However, the rapid growth of such black holes in the early universe suggests that the mechanisms of growth could be more complex than previously imagined. It's also possible that the environment in which these black holes formed played a crucial role in their rapid development. In the case of TON 618, it's possible that the black hole grew rapidly by accreting large amounts of gas and matter from its surroundings. As this material spirals into the black hole, it forms an accretion disk that generates immense energy, which we observe as a quasar. Over time, the black hole could have continued to feed on surrounding material, growing larger and larger. Another intriguing aspect of supermassive black holes like TON 618 is their role in regulating galaxy formation. While we often think of black holes as destructive forces, their gravitational influence may help shape the galaxies around them. In some cases, black holes can provide a stabilizing force, preventing the collapse of gas clouds and allowing stars to form. In other instances, the intense radiation from a quasar can have the opposite effect, driving away gas and halting star formation. The interaction between black holes and their host galaxies is a complex and dynamic process, one that may hold the key to understanding the evolution of galaxies over time. One of the most fascinating theories about supermassive black holes like TON 618 is their potential to act as cosmic engines, powering the creation of large-scale structures in the universe. By releasing enormous amounts of energy in the form of radiation and relativistic jets, black holes could influence the formation of galaxies, stars, and even the large-scale structure of the universe itself. This concept, known as feedback, suggests that black holes play an active role in shaping the cosmic landscape. As TON 618 continues to be studied, astronomers are beginning to understand the ways in which it might be shaping the surrounding space. The energetic jets emitted by quasars like TON 618 can have a profound impact on the surrounding gas and dust, pushing material out of the galaxy and influencing star formation. This feedback process is thought to play a significant role in regulating the growth of galaxies, and by studying TON 618 and other supermassive black holes, scientists are gaining valuable insights into how galaxies evolve over time. In addition to its role in galaxy formation, TON 618 also provides a unique opportunity to study the most extreme physical conditions in the universe. The immense gravitational forces near the event horizon of a supermassive black hole create an environment where space and time are warped to their absolute limits. Understanding how matter behaves in such extreme conditions is crucial for testing the limits of our current theories of physics. For example, the study of black holes can provide insights into the nature of gravity, the behavior of matter under extreme pressure, and even the possibility of new physics beyond the standard model. One of the most pressing questions that TON 618 and other supermassive black holes raise is the issue of the singularity. According to general relativity, the core of a black hole, the singularity, is a point of infinite density, where the laws of physics break down. However, this idea of an infinite singularity conflicts with quantum mechanics, which suggests that infinities are unphysical and should be avoided. This discrepancy between general relativity and quantum mechanics has led to the search for a unified theory of quantum gravity, which could provide a better understanding of the behavior of black holes at the quantum level. The singularity at the heart of TON 618 may not be a true point of infinite density, but rather a region where our current understanding of physics breaks down. Some theories suggest that quantum effects could modify the nature of the singularity, potentially leading to a finite, yet extremely dense region at the center of the black hole. This idea is supported by the concept of the fuzzball, a proposed structure that replaces the singularity with a quantum object made up of tangled strings of energy. The study of TON 618 also offers the possibility of exploring new avenues of physics beyond the standard model. For example, the extreme conditions near the event horizon of a black hole could provide insights into the behavior of dark matter, dark energy, and other exotic particles. Some physicists have proposed that black holes could act as laboratories for testing new theories of physics, such as string theory, loop quantum gravity, and other approaches to quantum gravity. As our understanding of TON 618 deepens, we may also gain new insights into the broader structure of the universe. Supermassive black holes like TON 618 are thought to be the engines that drive the formation of quasars, which in turn shape the evolution of galaxies. By studying the most massive black holes in the universe, we may learn more about the birth and death of galaxies, the formation of large-scale structures, and the role of black holes in the cosmic ecosystem. The discovery of TON 618 has also sparked interest in the search for other ultramassive black holes in the distant universe. As new telescopes and observational techniques come online, astronomers will be able to look deeper into the past and potentially uncover even more extreme black holes. The study of these objects will not only help us understand the nature of black holes but also provide a better understanding of the universe's evolution over cosmic time. But perhaps the most intriguing aspect of TON 618 is its potential to teach us about the ultimate fate of the universe. Black holes like TON 618 are the end result of the gravitational collapse of massive stars, and their study may offer insights into the life cycles of stars and galaxies. By understanding how black holes form and grow, we can learn more about the processes that govern the evolution of the universe as a whole. As TON 618 continues to captivate astronomers and physicists alike, it reminds us that the universe is filled with wonders beyond our comprehension. Objects like this black hole stretch the limits of our imagination and challenge our understanding of the laws of nature. As we continue to study TON 618 and its mysterious surroundings, we may find answers to some of the most profound questions in science, or perhaps encounter even more mysteries that will push the boundaries of human knowledge. The study of TON 618 also beckons us toward the frontier of theoretical astrophysics, where scientists push the boundaries of our understanding of the universe. In the quest to comprehend such enormous objects, new mathematical models and frameworks will undoubtedly emerge. As we attempt to uncover the underlying mechanisms driving the formation of black holes and their growth over cosmic timescales, TON 618 stands as a key point of focus, offering a chance to test our understanding of everything from gravity to quantum mechanics. We know that black holes, especially supermassive ones like TON 618, are not merely passive entities in the universe. They influence their environments in ways that go far beyond simply swallowing matter. The impact of these colossal forces can extend far beyond their immediate surroundings, affecting the galaxy in which they reside. For example, the energy emitted by the accretion disk of a supermassive black hole, radiation so intense that it can outshine the collective light of all the stars in a galaxy, can have a profound influence on star formation and the overall evolution of galaxies. This energy, carried in the form of electromagnetic radiation and relativistic jets, serves to regulate the amount of gas available for new stars to form. This feedback mechanism, where a black hole both influences and is influenced by the environment around it, is crucial for our understanding of the role black holes play in galactic evolution. Some astronomers suggest that black holes like TON 618 might even be a driving force behind galaxy formation itself. As the black hole exerts its immense gravitational pull, it creates a dynamic environment in which the gas clouds and stars that make up the galaxy must continually interact with the black hole's powerful energy emissions. This balance between accretion and radiation may govern not only the growth of the black hole itself but also the pace at which stars are born and die in the surrounding galaxy. Moreover, TON 618's sheer mass brings up intriguing questions about the physics of matter under extreme conditions. The black hole's influence is so strong that it distorts the fabric of spacetime itself, curving the path of light and creating phenomena that we can only begin to understand. This bending of light near the event horizon is so intense that it challenges our classical understanding of space and time, forcing scientists to think beyond the confines of general relativity. The extreme gravitational forces near TON 618 could offer new insights into the nature of spacetime itself, potentially revealing new aspects of physics that remain hidden in more normal environments. Additionally, TON 618's existence raises fundamental questions about the limits of black holes' size and the role of accretion in their growth. How does such a massive black hole accumulate so much mass in such a relatively short period of time in the cosmic timeline? What mechanisms allow for such rapid growth, even in the early universe, when it was believed that black holes might have had a much slower accumulation rate? These questions are essential for advancing our understanding of the formation and growth of supermassive black holes and, by extension, the galaxies in which they reside. As we continue to delve deeper into the study of objects like TON 618, we find ourselves asking about the very nature of the universe itself. This black hole exists at the extreme end of the spectrum of cosmic phenomena, and it might just hold the keys to some of the universe's most profound secrets. How did such an object form so early in the history of the universe? What can it teach us about the large-scale structure of the cosmos and the early moments following the Big Bang? Looking ahead, future missions to study supermassive black holes could help answer some of these burning questions. Missions like the Event Horizon Telescope, EHT, which aims to capture the first-ever image of a black hole's event horizon, could potentially offer new insights into the properties of black holes like TON 618. These advanced observational techniques might allow us to observe black holes in greater detail, providing unprecedented views of the accretion process, jet formation, and the surrounding material that contributes to their immense mass. The study of black holes like TON 618 is not merely an academic pursuit. It is a way for humanity to stretch the limits of what we know and explore the fundamental mysteries of the cosmos. Each new discovery takes us one step closer to understanding how the universe works on its largest scales, from the birth of galaxies to the extreme environments near the event horizon of a black hole. The more we learn about TON 618, the more we realize how much we still have to uncover about the nature of black holes, the formation of galaxies, and the evolution of the universe itself. As astronomers continue to study TON 618, the hope is that it will eventually lead us to a unified theory of physics, one that can reconcile general relativity with quantum mechanics and answer some of the deepest questions in science. Could the mysteries of TON 618 hold the key to understanding the very fabric of space and time? Could it help us discover new forms of matter, energy, or forces that we have yet to detect? The journey into the heart of TON 618 is far from over, and as we peer deeper into the cosmos, we are bound to encounter more questions, more enigmas, and more opportunities to expand our understanding of the universe. One thing is certain: the study of TON 618 will continue to captivate the imagination of astronomers, physicists, and anyone with a fascination for the mysteries of space. It stands as a testament to the wonders that still await discovery, urging us to reach further and think bigger about the ultimate nature of the cosmos. TON 618 reminds us of the incredible scale of the universe, where objects exist that are so massive, so powerful, that they defy comprehension. It challenges our understanding of the universe's birth, its evolution, and the very principles of physics that govern it. And perhaps, as we continue to study this awe-inspiring object, we will unlock the answers to questions that have perplexed humanity for millennia. TON 618, the most massive known black hole, is not just an astronomical object. It is a symbol of the vastness of the unknown, a cosmic riddle that continues to elude our full understanding but also pushes us forward into the depths of discovery. As we look toward the future of black hole research, the implications of TON 618 stretch far beyond our current understanding. While its sheer size is a remarkable feat of nature, it's the potential it holds to reshape our knowledge of the universe that makes it truly extraordinary. This black hole serves as a focal point for a host of astronomical and physical questions, each one more exciting than the last. The more we learn about TON 618, the more we are reminded that the universe is full of surprises, many of which are waiting to be discovered just beyond the reach of our current understanding. As we look beyond the theoretical implications of studying TON 618, it becomes apparent that this black hole also invites us to consider the future of space exploration. Although TON 618 lies at an unimaginable distance from Earth, about 10.37 billion light-years away, it continues to provide valuable insights into the nature of distant objects. The enormous size and mass of this black hole act as an astrophysical laboratory, offering a natural setting for testing the most fundamental aspects of physics under extreme conditions. One aspect of TON 618 that particularly fascinates scientists is the fact that it resides within a quasar, a highly energetic and active region of space. Quasars are some of the most luminous and powerful objects in the universe, and they are believed to be powered by supermassive black holes at their centers. The energy output of these quasars is so intense that they can be observed from billions of light-years away, making them critical objects of study in the field of astronomy. TON 618's quasar is one of the brightest known in the universe, and this provides astronomers with a unique opportunity to study a black hole in its active phase. In particular, the study of the quasar's energy output allows researchers to investigate the processes that occur near the event horizon of a black hole. It's this region where the gravitational pull of the black hole becomes so strong that not even light can escape, and it's this area that continues to challenge our understanding of how matter and energy behave under extreme gravitational forces. The accretion disk surrounding the black hole generates immense heat as matter spirals inward, emitting radiation across the electromagnetic spectrum. TON 618's quasar shines particularly brightly in ultraviolet and X-ray wavelengths, and this provides astronomers with an invaluable opportunity to study the properties of black holes and their surrounding environment in unprecedented detail. Beyond these immediate observations, the study of quasars like TON 618 also offers crucial insights into the formation and evolution of galaxies. It is widely believed that supermassive black holes, such as TON 618, play a pivotal role in shaping the galaxies in which they reside. They influence star formation rates, regulate the distribution of gas, and even impact the overall structure of the galaxy. Understanding how TON 618's quasar interacts with its host galaxy will help scientists gain a deeper understanding of how galaxies form and evolve over cosmic time scales. In addition to these cosmological implications, TON 618 serves as a gateway to understanding the limits of black hole growth. One of the most pressing questions in modern astrophysics revolves around how supermassive black holes grow to such extraordinary sizes. Given that TON 618's mass is over 66 billion times that of our Sun, scientists are naturally curious about the mechanisms that drive such growth. Was this black hole able to accumulate such mass through the accretion of gas and matter over time, or is there another, more exotic mechanism at play? Could TON 618 have formed rapidly in the early universe, possibly through the merging of smaller black holes or the direct collapse of a massive cloud of gas? The mystery surrounding the growth of supermassive black holes is further complicated by the fact that many of these objects, including TON 618, are found at the centers of quasars. It's believed that the black hole's rapid growth occurs alongside the intense radiation produced by the accretion of gas, but the exact relationship between these processes is still not fully understood. TON 618, with its incredible luminosity and size, presents an ideal test case for exploring these issues, offering researchers a glimpse into the early stages of black hole growth and shedding light on the mechanisms that drive such extreme cosmic phenomena. Understanding the processes that lead to the formation of supermassive black holes like TON 618 also ties into broader questions about the evolution of the universe. Supermassive black holes are thought to play a critical role in the development of large-scale structures in the universe, such as galaxies and clusters of galaxies. The radiation and gravitational effects of these black holes can influence the movement of gas and stars within their host galaxies, and these interactions, in turn, have profound implications for the formation and evolution of galactic systems. One particularly interesting aspect of TON 618 is its location in the early universe, approximately 10.37 billion light-years away. This places it in a time period just a few billion years after the Big Bang. It is a direct window into the conditions of the early cosmos, and the fact that such an incredibly massive black hole exists so early in the universe's history raises important questions about the formation of supermassive black holes. Did TON 618 form quickly after the Big Bang, or was it the result of a series of mergers and accretions over a much longer period of time? Understanding the formation of supermassive black holes like TON 618 could also help us better understand the evolution of the universe itself. As these black holes grow and evolve, they release enormous amounts of energy that can influence the behavior of surrounding matter, particularly gas clouds. The feedback mechanisms produced by these black holes can regulate star formation, leading to changes in the structure of galaxies and the distribution of matter. By studying TON 618, we gain insight into these cosmic processes and learn more about the way galaxies evolve over time. Another compelling feature of TON 618 is its connection to the mystery of dark matter and dark energy. While TON 618 itself is a visible and observable object, it may still hold clues to the nature of these enigmatic components of the universe. Dark matter, which is thought to account for the majority of the mass in the universe, and dark energy, which is responsible for the accelerated expansion of the cosmos, are still poorly understood. However, the gravitational influence of supermassive black holes like TON 618 may provide indirect evidence for the existence and properties of dark matter and dark energy. For example, the motion of stars and gas clouds near TON 618 may be influenced by the presence of dark matter, and this could offer clues to its distribution in the galaxy and the broader universe. Similarly, the study of TON 618's growth and behavior may offer insights into the nature of dark energy. As black holes like TON 618 grow, they release tremendous amounts of energy that could have a profound effect on the surrounding universe. This energy may interact with dark energy, which is thought to be responsible for the accelerated expansion of the universe, and this interaction could help us better understand the relationship between these two mysterious forces. In the coming decades, as our observational capabilities improve, the study of TON 618 will undoubtedly continue to yield new insights into some of the most fundamental questions in astrophysics. The development of next-generation telescopes, such as the James Webb Space Telescope, JWST, will allow us to study supermassive black holes in greater detail than ever before. These advancements in technology could lead to breakthroughs in our understanding of the formation and growth of black holes, as well as their role in the evolution of galaxies and the universe as a whole. As we look further into the depths of space, TON 618 remains an awe-inspiring reminder of the immense scale and complexity of the universe. Its discovery and continued study push the boundaries of human knowledge, offering a glimpse into the most extreme environments in the cosmos. The mystery of this massive black hole, and the insights it may one day reveal, will continue to captivate astronomers and astrophysicists for generations to come. TON 618 is not just a cosmic oddity. It is a window into the unknown, a place where the laws of physics break down, and where the most profound mysteries of the universe await. Its size, power, and ability to challenge our understanding of the cosmos make it one of the most exciting objects in modern astronomy. And as we continue to explore its secrets, we will undoubtedly unlock new chapters in the story of the universe's origin, evolution, and ultimate fate. TON 618's fascinating characteristics, both as a supermassive black hole and a powerful quasar, place it in the spotlight of modern astrophysical research. But the questions surrounding its formation and evolution persist, and the more we learn about it, the more we realize how much there still is to uncover. While TON 618 has become a key piece in our understanding of supermassive black holes, its role as a cosmic probe into the history of the universe may be far from complete. Each discovery adds new layers of complexity to the mystery of the universe's most massive objects. One of the most intriguing aspects of TON 618 is its formation. A question that continues to baffle scientists is how such an enormous black hole came into existence so early in the universe's history. With its mass of 66 billion solar masses, TON 618 is far more massive than most supermassive black holes that have been observed, and it resides at a time when the universe was still young, merely 10.37 billion years ago. For comparison, our own Milky Way galaxy's supermassive black hole, Sagittarius A, is a mere 4 million times the mass of our Sun. The existence of such a supermassive black hole this early in the universe is a challenge to current models of black hole growth, and it forces astronomers to reconsider the timeline and processes of black hole formation. There are a variety of theories about how TON 618 and other similar supermassive black holes might have formed in the early universe. One prominent theory is the direct collapse model, which proposes that supermassive black holes could form from the collapse of large gas clouds in the early universe. These gas clouds would have been much larger and denser than the clouds of gas we observe today, allowing them to collapse directly into black holes without the intermediate steps seen in more typical stellar black hole formation. If TON 618 formed through this mechanism, it would provide an important clue about the early conditions of the universe and the potential for black holes to grow rapidly in the first few billion years after the Big Bang. Another theory suggests that supermassive black holes like TON 618 could have grown through the accretion of gas over time, starting from a much smaller seed black hole and gradually gaining mass by pulling in surrounding matter. However, the rapid growth of TON 618 presents a challenge to this model, as it would require an enormous amount of gas to fall into the black hole in a relatively short period of time. The accretion rate required for such rapid growth would have to be extraordinarily high, and yet the surrounding environment of TON 618 seems to be relatively stable, suggesting that this process may not be the sole contributor to its formation. In addition to these theories, the merging of smaller black holes is another possible explanation for the existence of supermassive black holes. This theory posits that over time, smaller black holes could collide and merge, eventually forming a larger supermassive black hole. If TON 618 grew in this way, it would be an example of how black holes can evolve through hierarchical mergers, a process that could have occurred on a cosmic scale throughout the history of the universe. While the merger hypothesis is supported by some evidence, it also presents challenges, as the dynamics of such mergers are complex, and we would expect to see some evidence of these interactions in the surrounding environment of the black hole. Despite the challenges in understanding how TON 618 formed, one thing is clear: Its existence challenges our understanding of the conditions that led to the formation of supermassive black holes. TON 618 provides a unique opportunity to study the growth mechanisms of black holes, offering a glimpse into the processes that shape the universe as we know it. Understanding how it grew so massive so quickly could provide key insights into the early history of the universe, the development of galaxies, and the processes that govern the formation of supermassive black holes. The study of TON 618 is not limited to understanding its formation, however. The immense energy radiated by this quasar offers a rich source of data for astronomers. The radiation emitted by the accretion disk surrounding the black hole is one of the most powerful sources of light in the universe. This energy allows scientists to study the inner workings of black holes in unprecedented detail, examining how matter behaves near the event horizon, where the gravitational pull becomes so strong that not even light can escape. TON 618's quasar emits radiation across the electromagnetic spectrum, from radio waves to X-rays. This broad spectrum of energy allows astronomers to observe the quasar in a variety of ways, each revealing different aspects of the black hole's environment. In particular, the study of the X-ray emissions from the quasar provides valuable information about the temperature and density of the material surrounding the black hole. These observations can help us understand the behavior of the accretion disk, the structure of the black hole's event horizon, and the complex processes that take place in the region where matter is rapidly falling in. X-ray emissions are produced when matter in the accretion disk is heated to extreme temperatures by the intense gravitational forces at work near the black hole. The temperatures in this region can reach millions of degrees, causing the gas to emit high-energy radiation as it spirals inward. By studying the X-ray emissions from TON 618, scientists can learn more about the rate at which the black hole is accreting matter, as well as the structure of the accretion disk itself. These observations can also provide clues about the nature of the black hole's event horizon, as the emission of X-rays is influenced by the behavior of light near the event horizon. TON 618 also provides a natural laboratory for studying the dynamics of black hole jets. Many supermassive black holes, including TON 618, are surrounded by powerful jets of relativistic particles that are expelled at nearly the speed of light. These jets are thought to be produced by the interaction of magnetic fields near the black hole, and they can extend vast distances from the center of the galaxy. The study of black hole jets is a rapidly growing field in astrophysics, and TON 618 offers a prime example of how these jets are formed and how they interact with the surrounding environment. By studying the properties of the jets emitted by TON 618, scientists can learn more about the magnetic fields near the black hole and the role these jets play in the regulation of the galaxy's gas and star formation processes. Beyond its contributions to the study of black holes, TON 618 also has implications for our understanding of the large-scale structure of the universe. As mentioned earlier, supermassive black holes like TON 618 are thought to play a significant role in the evolution of galaxies. The energy released by the accretion of matter and the interaction of black hole jets with their host galaxy can have a profound effect on the surrounding gas, regulating star formation and shaping the overall structure of the galaxy. The study of TON 618's quasar provides valuable information about these processes, helping astronomers understand how black holes influence their host galaxies and how galaxies evolve over time. TON 618's quasar is one of the most luminous in the universe, and its study could provide important insights into the processes that power quasars in general. While quasars are typically thought to be powered by supermassive black holes, there is still much we don't know about the exact mechanisms behind their extreme energy output. TON 618's quasar, with its enormous luminosity and exceptional energy emissions, provides a rare opportunity to study the dynamics of these objects in detail. By studying the radiation emitted by TON 618's quasar, scientists hope to uncover new clues about the nature of quasars, the processes that power them, and their role in the formation and evolution of galaxies. As we continue to push the boundaries of our observational capabilities, the study of objects like TON 618 will become increasingly important. With the advent of new and more powerful telescopes, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, we will be able to observe even more distant and faint objects than ever before. These advancements in technology will enable astronomers to probe the nature of supermassive black holes like TON 618 in unprecedented detail, shedding light on the processes that govern their formation, growth, and behavior. It will also allow us to explore the broader implications of these discoveries, such as their impact on galaxy formation and the evolution of the universe as a whole. In the coming years, as we continue to observe and study TON 618, we are likely to uncover even more extraordinary revelations about the nature of supermassive black holes, the quasars they power, and the forces that drive the evolution of the universe. The study of these cosmic giants is still in its early stages, and there is no telling what new discoveries await us as we push the limits of our understanding of the cosmos. As the study of TON 618 progresses, one of the most exciting aspects is the potential it holds for furthering our understanding of black holes in general. Its extreme size and energy output provide a unique testing ground for a variety of theories in astrophysics. For example, one area of active research is the potential connection between the formation of supermassive black holes and the overall structure of the universe. Some scientists suggest that these massive black holes might not only influence the formation and evolution of their host galaxies, but they could also play a key role in shaping the large-scale distribution of matter in the universe. If TON 618 formed through direct collapse, as some models suggest, it could offer a glimpse into the early universe, when the first black holes were beginning to form. These early black holes would have been crucial in helping shape the structure of the cosmos. They could have helped seed the formation of galaxies and influenced the distribution of dark matter, which remains one of the most elusive components of the universe. The discovery of a supermassive black hole like TON 618 in such an early stage of the universe provides compelling evidence that black holes may have formed rapidly, altering the course of cosmic evolution in their wake. The relationship between supermassive black holes and the galaxies that host them is another area of research that has seen substantial progress due to the study of TON 618. Observations have shown that most galaxies contain supermassive black holes at their centers, and that the size of these black holes is strongly correlated with the size of the galaxy. This correlation, known as the M-sigma relation, suggests that the growth of a supermassive black hole and the evolution of its host galaxy are intimately connected. In the case of TON 618, its quasar activity might be shedding light on the feedback mechanisms that regulate galaxy formation. The enormous energy released by the accretion disk can expel material from the surrounding galaxy, halting star formation and potentially even preventing the formation of new black holes. The jets emitted by TON 618 also provide an opportunity to study the role of black hole-driven outflows in shaping the intergalactic medium. As the jets travel outward, they can collide with surrounding gas, compressing it and triggering star formation in some cases, while also heating and expelling gas in others. These complex interactions between black holes and galaxies form the foundation of our current understanding of galaxy evolution. TON 618's quasar and its interaction with its host galaxy could provide crucial insights into these processes. It is not just a passive object but an active participant in the ongoing evolution of its environment. Through a better understanding of how TON 618 interacts with its surroundings, we can gain a deeper insight into how supermassive black holes influence their host galaxies and the broader universe. Moreover, TON 618 challenges the conventional wisdom on the growth rates of supermassive black holes. Typically, supermassive black holes are thought to grow slowly over billions of years, accumulating mass in a steady fashion as they accrete matter from their surroundings. However, the extraordinary size of TON 618 suggests that it may have grown at an accelerated pace. The processes that allowed it to accumulate such a massive amount of matter in such a short amount of time remain a topic of great interest. In the early universe, conditions were quite different from what we observe today, with vast clouds of gas and the absence of significant cosmic structures like galaxy clusters. This allowed black holes to accrete at much higher rates, possibly explaining the rapid growth of TON 618. TON 618's discovery also sparks new discussions about the potential for even more massive black holes to exist. If TON 618 represents a supermassive black hole in its prime, it is conceivable that there are other black holes in the universe that are even more massive, yet still undetected. The search for these objects has become an increasingly important goal for astronomers. The discovery of an even larger black hole would push the boundaries of our understanding of black hole growth and the limits of their formation. While the size of TON 618 is staggering, it is also essential to explore the implications of its extreme luminosity. The quasar at the heart of TON 618 emits an intense stream of radiation, making it one of the brightest objects in the universe. This radiation is primarily driven by the immense gravitational forces exerted by the black hole as it pulls in surrounding gas and dust. As this matter falls into the black hole, it heats up, emitting energy across the electromagnetic spectrum, from visible light to X-rays. The intense brightness of TON 618's quasar provides an opportunity for astronomers to study the extreme conditions near the event horizon. The event horizon is the point beyond which nothing, not even light, can escape the gravitational pull of the black hole. As matter approaches the event horizon, it is stretched and compressed by the black hole's gravity, a process known as spaghettification. This extreme tidal force can cause the gas and dust in the accretion disk to emit radiation, which can then be observed from Earth. By studying the radiation emitted by TON 618, scientists are able to gain valuable insights into the behavior of matter near the event horizon. The emissions reveal the dynamics of the accretion disk, including its temperature, density, and structure. By examining these characteristics, astronomers can gain a better understanding of how black holes accrete matter and how energy is produced in the process. These observations are essential for refining models of black hole growth and accretion, helping us to better understand the processes that govern the behavior of the most massive objects in the universe. Another aspect of TON 618 that is of great interest to astronomers is its size relative to other known supermassive black holes. While TON 618 is an extreme example, it is not alone in the universe. Supermassive black holes are thought to reside at the centers of most large galaxies, including our own Milky Way. The size of these black holes varies, with some being relatively small, on the order of a few million solar masses, and others, like TON 618, reaching extreme masses on the order of tens of billions of solar masses. Despite the vast differences in size, all supermassive black holes appear to share certain characteristics, particularly when it comes to their behavior and their interactions with their host galaxies. The relationship between the mass of the black hole and the size of the galaxy's bulge, for example, is a well-established correlation known as the M-sigma relation. TON 618's extreme mass and its quasar activity provide an opportunity to study this relationship in detail, shedding light on the role of black holes in shaping the galaxies that host them. As the study of TON 618 continues, it is likely that new discoveries will be made that further challenge our understanding of black holes and the universe itself. The incredible mass, luminosity, and energy emissions of TON 618 make it one of the most fascinating objects in astrophysics today. It is not just an isolated phenomenon, but a key player in the ongoing evolution of galaxies and the universe as a whole. By continuing to study TON 618, we can hope to uncover new insights into the formation and growth of supermassive black holes, the nature of quasars, and the broader processes that shape the cosmos. As we peer deeper into the universe, TON 618's mysterious and awe-inspiring nature will continue to captivate astronomers and researchers. The black hole's unusual properties present new challenges and new opportunities to explore the fundamental forces that govern the universe. Each discovery brings us one step closer to unlocking the secrets of these cosmic giants, and TON 618 remains one of the most promising objects for future study. The immense size and energy of TON 618 continue to fascinate scientists, and as research into its properties progresses, we can expect to uncover even more surprising revelations. The universe's vastness means that we are only just beginning to scratch the surface when it comes to understanding the full scope of black holes like TON 618. Its immense gravitational pull, the way it influences the surrounding spacetime, and its incredible luminosity are not only important for theoretical astrophysics, but are crucial for the development of new models and technologies in the field. One of the most captivating aspects of black holes in general, and TON 618 in particular, is the way they challenge our understanding of physics. General relativity, the theory proposed by Albert Einstein in 1915, successfully explains the behavior of black holes in most cases. However, when you push the limits of our understanding, such as in the case of TON 618, we find that there are still gaps in our knowledge. The discovery of objects like TON 618 forces us to reconcile general relativity with quantum mechanics, a long-standing challenge in physics. This has led to efforts to formulate a theory of quantum gravity, which could help bridge the gap between these two pillars of modern physics. The combination of general relativity's predictions about the behavior of spacetime around a black hole and quantum mechanics' descriptions of the behavior of particles on the smallest scales presents significant difficulties. When looking at a supermassive black hole like TON 618, we encounter the problem of understanding what happens at the singularity, the point at the very center of the black hole where matter is believed to collapse to infinite density, and the laws of physics, as we currently understand them, cease to function normally. These mysterious regions have long been a subject of fascination, as they represent the limits of our knowledge and the frontiers of scientific discovery. In particular, the study of TON 618 and other supermassive black holes might provide clues about the behavior of matter and energy under extreme conditions. Understanding how quantum effects operate near the event horizon could offer unprecedented insights into the true nature of spacetime itself. Some researchers believe that quantum effects might even allow black holes to leak information, in defiance of the traditional information paradox that suggests information falling into a black hole is lost forever. This is a contentious issue that has led to much debate in the physics community, with different theories suggesting various ways in which information might be preserved despite the apparent loss of all known information inside a black hole. TON 618's extreme size and powerful radiation output allow researchers to study phenomena that could answer some of the fundamental questions about the nature of space and time. For example, TON 618 provides an excellent testing ground for the study of Hawking radiation, a theoretical process that suggests black holes can emit radiation due to quantum effects near the event horizon. Though Hawking radiation has never been directly observed, it offers a potential solution to the information paradox, and studying supermassive black holes like TON 618 might eventually lead to breakthroughs in our understanding of this phenomenon. As astronomers continue to improve their observation techniques and technological capabilities, they are pushing the boundaries of what we can learn about black holes. Future space telescopes and observatories will likely provide even more detailed information about TON 618 and other black holes, allowing us to map their surroundings in unprecedented detail. New techniques, such as gravitational wave astronomy, have already opened a new window into the study of black holes. Gravitational waves, the ripples in spacetime caused by massive objects like merging black holes, could provide further insights into the behavior of these cosmic giants. Another exciting possibility is the application of advanced simulations and artificial intelligence to study the behavior of black holes. With the help of supercomputers, scientists are able to model the behavior of matter near the event horizon of a black hole, predicting how gas, dust, and even light behave under the influence of such immense gravitational forces. AI is now being utilized to analyze vast amounts of observational data, such as the images produced by the Event Horizon Telescope, which captured the first ever image of a black hole in 2019. As these technologies evolve, they will allow for even more detailed and accurate simulations of the behavior of black holes like TON 618, leading to a deeper understanding of their complex nature. The study of TON 618 is not only significant for understanding the mechanics of black holes, but also for the larger field of cosmology. By analyzing the properties of quasars, scientists can learn more about the early universe, as the light from TON 618 has traveled billions of years to reach us. Observing quasars is like looking into a cosmic time capsule, offering a glimpse of the conditions that existed in the universe when it was much younger. TON 618, with its enormous size and activity, may hold the key to understanding how the universe evolved from its earliest stages to the present day. Furthermore, The discovery of TON 618 may help scientists understand the processes that govern the formation of supermassive black holes in the first place. While we know that most galaxies harbor supermassive black holes at their centers, the exact process of their formation remains a topic of much debate. Did they form from the collapse of massive gas clouds, or were they seeded by the merger of smaller black holes? How did they grow to such enormous sizes, and what role did the surrounding galaxy play in their development? By studying TON 618, scientists can gain important clues that will help unravel these mysteries. While TON 618 is one of the largest known black holes, it is possible that even more massive black holes exist, waiting to be discovered. The discovery of such objects would undoubtedly lead to new questions and theories in astrophysics, as the sheer scale of these objects defies our current understanding of black hole formation and growth. As observational technology continues to advance, astronomers are likely to uncover even more supermassive black holes, some of which could rival or even exceed the size of TON 618. The discovery of these objects is not just important for understanding black holes, but for our broader understanding of the universe. By studying objects like TON 618, we can learn more about the forces that shape galaxies, the role of dark matter, and the nature of the early universe. The study of black holes is a window into some of the most fundamental questions in physics and cosmology. As we continue to explore the mysteries of the cosmos, TON 618 will undoubtedly remain one of the most intriguing objects in the universe, offering us a glimpse into the very heart of one of the most powerful and enigmatic phenomena in the cosmos. Despite the extraordinary advances in our understanding of black holes, many questions remain unanswered. What happens inside a black hole's event horizon? Is there a connection between the formation of supermassive black holes and the larger structures of the universe? And what role do they play in the evolution of galaxies? These are questions that will likely occupy astronomers and physicists for decades to come, and TON 618 is poised to be a key object in this ongoing search for answers. Through continued observation and research, we may one day unlock the full mysteries of TON 618 and other supermassive black holes, and in doing so, gain a deeper understanding of the very fabric of the universe itself. The future of black hole research, particularly with regards to TON 618, is filled with promise and potential discoveries that could reshape our understanding of the universe. As technology improves, our ability to observe these cosmic giants and understand their behavior will continue to evolve. One of the most exciting areas of research in this field is the study of gravitational waves. Gravitational wave astronomy, which has gained significant attention in recent years due to groundbreaking discoveries, opens up an entirely new way of studying the universe. Gravitational waves are ripples in spacetime created by massive objects, like black hole mergers, that travel outward from their source. When two black holes, such as those that are found in binary systems or even supermassive black holes like TON 618, merge, they generate gravitational waves that can be detected by observatories on Earth. The detection of gravitational waves provides a wealth of information that was previously impossible to obtain. It allows scientists to measure the mass, spin, and trajectory of black holes that may be billions of light years away. Moreover, these waves can offer insights into the very nature of spacetime, as they provide a direct glimpse of the fabric of the cosmos itself. When applied to TON 618, gravitational wave observations could reveal new details about its structure and dynamics, shedding light on the behavior of the enormous black hole and its accretion disk. The data collected could also help us understand how black holes grow and evolve over time, and whether processes like accretion and merger contribute to their massive sizes. The study of black holes like TON 618 is not just confined to theoretical and observational astrophysics. It also holds profound implications for our understanding of other scientific fields. One such area is the study of dark matter. Dark matter, which makes up a significant portion of the universe's mass, remains one of the greatest mysteries in science. It does not emit light or any form of electromagnetic radiation, making it invisible to conventional telescopes. However, the gravitational effects of dark matter are evident, as they influence the motion of galaxies and galaxy clusters. Ton 618's enormous gravitational pull provides an excellent environment to study the effects of dark matter on a cosmic scale. Black holes themselves might even be able to help us detect dark matter, particularly in the context of dark matter halos, the invisible spheres of dark matter that are thought to surround galaxies and their central black holes. These halos could influence the behavior of matter within the accretion disk and might play a role in the growth and evolution of supermassive black holes like TON 618. Investigating the relationship between dark matter and black holes could help scientists probe the properties of this elusive substance, and TON 618, with its massive size and strong gravitational field, provides a powerful natural laboratory for studying this connection. Another area in which TON 618 could provide groundbreaking insights is the study of cosmic inflation. Theories of inflation suggest that the universe underwent a rapid expansion in the moments immediately after the Big Bang, leading to the large-scale structure we observe today. Understanding how black holes, particularly supermassive ones like TON 618, relate to the cosmic expansion and the evolution of galaxies could provide clues about the early universe. If black holes played a significant role in the early stages of the universe, their formation and growth could have been influenced by the same processes that governed cosmic inflation. This is a relatively unexplored area of research, but with new technologies and more powerful telescopes, scientists are beginning to look for signs of such connections. In addition to the scientific implications, the study of TON 618 and other supermassive black holes also has the potential to inspire future space missions and technological advancements. For example, as we continue to develop more sophisticated space observatories, such as the James Webb Space Telescope, scientists will be able to observe these distant cosmic objects in greater detail than ever before. These advancements could lead to new methods of probing the universe, allowing us to study black holes and other extreme cosmic phenomena in ways that were once thought to be impossible. One such future mission that could enhance our study of TON 618 and other supermassive black holes is the proposed Event Horizon Telescope, EHT, expansion. The EHT, which produced the first ever image of a black hole in 2019, has the potential to capture even more detailed images of the event horizon, or the point of no return, of black holes like TON 618. This is crucial, as understanding the physics of the event horizon could reveal profound insights into the nature of space-time, quantum mechanics, and the behavior of matter under extreme gravitational forces. As more observatories join the EHT network, scientists will be able to construct a more accurate and detailed picture of supermassive black holes, including those located billions of light-years away, like TON 618. Another potential area of future research that could deepen our understanding of TON 618 involves the exploration of black hole mergers. While black hole mergers have already been observed through gravitational wave detections, the merger of supermassive black holes, such as those that could be involved with TON 618, remains a major area of study. These mergers can release immense amounts of energy, and the study of their aftermath could provide invaluable data about the dynamics of supermassive black holes. Additionally, observing the merging process of black holes could give us more insight into the conditions that led to the formation of black holes in the first place. Did the process involve the collapse of massive stars, or were primordial black holes, formed in the early universe, involved? By studying the results of these mergers, scientists can refine their models and better understand the history of the cosmos. TON 618's discovery and study also offer valuable perspectives on the concept of cosmic scale. We often think of the universe as a vast, incomprehensible expanse, but supermassive black holes like TON 618 remind us of the true scale of cosmic phenomena. The enormity of these objects forces us to reevaluate our place in the universe and our understanding of its structure. TON 618, with its immense mass and gravitational pull, challenges our conception of scale and introduces us to a universe far more complex and mind-boggling than we ever imagined. As the universe continues to expand and as our knowledge of black holes continues to grow, we will undoubtedly encounter more mysteries that challenge our understanding of space and time. TON 618 represents just one of many incredible objects that populate our universe, but it stands as a testament to the extremes that nature can produce. The sheer size and energy of TON 618 push the boundaries of human knowledge, providing a constant reminder that the universe is full of secrets waiting to be uncovered. With each new discovery, we inch closer to understanding the fundamental forces that govern the cosmos, and TON 618, with its extraordinary size, will undoubtedly continue to be a beacon in our quest to unlock the mysteries of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.